It begins with a story we all know, one that has been retold for more than 3 centuries. A man sits beneath an apple tree. The air is calm, the evening soft, and above him, the sky holds a silence older than time itself. Then, with no warning, an apple detaches from its stem and falls to the ground. For most people, this would be an ordinary moment. But to Isaac Newton, it was the spark that would reveal one of the deepest truths about the universe. Why does the apple fall? It seems such a simple question, yet in that simplicity lies the greatest mystery in all of nature. The story, whether literal or legend, marks the birth of our understanding of gravity, the first invisible force ever discovered by humankind. Until that moment, people knew that things fell, that stones dropped, that rain returned to the earth, that the moon circled endlessly above. But no one had ever truly asked why. Newton did not see the apple's fall as an isolated event. He saw a connection between the apple, the moon, and the heavens. He wondered, could the same force that pulls the apple downward also hold the moon in its orbit? Could one law bind both earth and sky? That question changed science forever. In the 17th century, the world was awakening to reason. Telescopes had only just begun to reveal the hidden precision of the cosmos. Galileo had watched moons orbit Jupiter, and Kepler had charted the geometry of planetary motion. But Newton went deeper. He imagined that every mass in the universe pulls on every other mass, with a force proportional to their weight and inversely proportional to the square of their distance. It was a stunning revelation. Suddenly, the same principle that explained why apples fall could also explain the motion of worlds. To Newton, gravity was not a material thing. It was a law of nature, a kind of invisible tether binding all objects together. And yet, there was something unsettling about his own discovery. He could describe how gravity behaves, but not what it truly was. When critics asked how the sun could pull the Earth across 93 million miles of empty space without anything between them, Newton could only answer, "I frame no hypotheses." He admitted that he did not know. The phrase, "action at a distance," was born. In Newton's vision, every particle of matter instantly influenced every other, no matter how far apart. There was no medium, no signal, no delay. The pull was immediate, as though the universe were one giant web of invisible threads. But this idea made many philosophers uneasy. Even Newton himself found it difficult to accept that a force could act across the void without any contact or carrier. The idea seemed almost mystical. How could the sun, burning in the distance, reach across empty space to guide the planets along their orbits? How could it exert a pull faster than any motion, faster even than light itself? For 2 centuries, no one could answer these questions. Newton's equations worked perfectly, predicting the paths of planets and the tides of the oceans with breathtaking accuracy. But they told us nothing about why gravity worked at all. In Newton's time, space was thought to be a simple, unchanging stage. Objects moved through it like actors on a theater floor, but the floor itself never moved. Gravity, it seemed, was an invisible thread drawn across this empty backdrop. The universe was a machine, precise and eternal, ruled by clockwork laws. But even this grand machine had its mysteries. If gravity was a pull between every pair of objects, then what carried that pull? How could something as intangible as a number in an equation reach across the emptiness of space? For centuries, scientists tried to fill that gap. Some imagined invisible particles or fluids that carried the gravitational effect, much like sound travels through air or ripples move across water. But no experiment could reveal such a medium. The space between stars remained perfectly silent. The pull remained unbroken, unmediated, instantaneous. This was gravity's paradox. We could measure its strength, feel its effects, and chart its precision, yet we could not touch it, see it, or isolate it. It was everywhere, and yet nowhere. The force that shaped galaxies and bound the cosmos together remained utterly invisible. As the 18th century unfolded, Newton's laws became the foundation of modern science. They guided the orbits of planets, predicted eclipses, and mapped the trajectories of comets. Sailors navigated by them. Engineers built bridges using them. The universe, it seemed, had finally yielded its secrets. But beneath that triumph lay a silent question that refused to die. What is gravity made of? If the universe is filled with forces, then perhaps those forces must be carried by something. Light, for example, travels as waves through electromagnetic fields. Sound moves through air. Heat spreads through molecules. But gravity acts through nothing. It simply is. For centuries, this idea stood unchallenged. It was elegant, useful, and true enough to send spacecraft to distant planets. But science is never satisfied with enough. The deeper we look, the stranger the universe becomes. And so, in the early years of the 20th century, a new mind began to question Newton's invisible threads. A man who saw time not as a constant, but as a pliable dimension. A man who would shatter the concept of absolute space itself. His name was Albert Einstein, and his revolution would transform gravity from a force into something far more profound, the very shape of reality. The century turned, and the world changed. Machines now roared where horses once trod. Light itself could be captured in photographs. The human mind had begun to conquer motion, distance, and even the air. Yet the question of gravity still lingered, unsolved and unsatisfied. Newton's equations described how planets moved, but they could not explain why their motion was bound to the pull of invisible attraction. In the heart of Europe, a young patent clerk in Bern began to imagine space and time not as separate things, but as threads of a single tapestry. Albert Einstein was only in his 20s when he proposed his special theory of relativity, showing that time could slow and distances could shrink depending on motion. It was a daring idea, one that shattered the comfortable world of absolute time. But Einstein was not done. He began to wonder about acceleration, about what it truly meant to fall. Suppose, he thought, a man is inside a sealed elevator, floating in deep space, far from any planet. If the elevator begins to accelerate upward, the man feels a force pressing his feet to the floor. Now suppose instead the elevator is at rest near the surface of the Earth. The man feels the same pressure on his feet, but this time it comes from gravity pulling him downward. How? Einstein asked. Could he tell the difference? This simple question led to one of the greatest insights in the history of physics. If acceleration and gravity feel the same, then perhaps they are the same. The force that pulls us toward the ground is not a force in the ordinary sense at all. It is the experience of moving through a curved geometry, the geometry of space-time itself. To most people, space had always been the emptiness between things, a nothingness. But Einstein saw it as something real, dynamic, and flexible. Mass and energy, he realized, could bend this space-time fabric, curving the paths of everything that moves through it. Planets orbit not because they are pulled by an invisible string, but because the sun's mass creates a valley in space-time, and the planets roll along the curves of that valley. In this picture, gravity is not made of a substance. It is the shape of the universe itself. The Earth does not tug at the moon. Rather, the moon moves along the curved path that Earth's mass creates. What we call gravitational attraction is simply motion through distorted geometry. It was an idea so radical that even Einstein struggled to accept its full implications. To express it mathematically, he needed to redefine geometry itself, using the language of curved surfaces and tensor equations. After nearly 10 years of struggle, he succeeded. In 1915, he published his general theory of relativity, the law of gravity rewritten as geometry. For the first time, gravity had a mechanism, though not the one Newton had imagined. The universe was no longer a static stage, but a living, bending fabric. And this fabric could ripple, stretch, and twist. When a planet or star moves, it changes the shape of space-time around it. The curvature moves outward at the speed of light, carrying information about the mass that caused it. Action at a distance was gone. Gravity now had a finite speed. Einstein's theory transformed our understanding of everything from starlight to time itself. Light passing near a massive star would bend along the curved geometry of space-time, creating a gravitational lens. Time would slow near heavy objects, making clocks tick more slowly at the surface of a planet than in empty space. Even the very concept of straight lines had to be redefined. In this new cosmos, geometry replaced force, and curvature replaced attraction. The universe was no longer governed by invisible pulls, but by the shape of reality itself. Space could warp, and time could twist. The fabric of existence was alive with motion. Yet even as Einstein's equations predicted a beautiful and consistent universe, they opened new mysteries. What was space-time made of? Could something bend and stretch if it had no substance at all? Was the fabric real, or merely a mathematical convenience? For centuries, scientists had asked what carries the gravitational force. Now the question had evolved into something deeper. What is space-time? Einstein's vision soon found proof. In 1919, British astronomers observed the bending of starlight during a solar eclipse exactly as his equations predicted. The universe had confirmed his dream. The newspapers declared that Newton's law had fallen. The sun no longer pulled planets with an invisible force. Instead, it sculpted the geometry of the cosmos. To the human mind, the idea was both magnificent and unsettling. If space and time could bend, what did that mean for the concept of distance, or of now, or of here? Reality itself had become elastic. The floor beneath our feet and the stars above our heads were woven into a single cosmic fabric. Einstein's theory was more than a scientific triumph. It was a new philosophy of the universe. It showed that the cosmos is not built from separate pieces, but from relationships between energy, matter, and geometry. To understand one is to understand them all. But the story of gravity does not end there. For while Einstein's equations could describe the universe on the grandest scales, stars, galaxies, and the expansion of space itself, they faltered in the world of the very small. In the atomic realm, a new revolution was taking shape. Quantum mechanics was emerging, painting a picture of reality built not from continuous curves, but from discrete quanta, tiny packets of energy and probability. It was a universe that flickered and jumped, uncertain and granular. When physicists tried to combine Einstein's curved spacetime with quantum mechanics particles and fields, the two refused to fit. One described smooth geometry, the other, restless quanta. The language of one could not translate into the mathematics of the other. The conflict was fundamental. Einstein's gravity was deterministic, continuous, and geometric. Quantum theory was statistical, discontinuous, and probabilistic. Together, they created a paradox, a universe governed by two laws that could not coexist peacefully. And so, the question returned, sharper than ever. If gravity is geometry, how can it also exist in a world made of quantum particles? Could there be a missing piece, a deeper framework uniting the two? If every other force in nature is carried by particles, the photon for electromagnetism, the gluons for the strong force, the W and Z bosons for the weak force, then what carries gravity? What if the smooth fabric of space-time is not continuous after all, but made of something smaller, something discrete? What if there exists a particle of gravity itself, a messenger that carries the information of curvature from one point to another? The search for that particle would consume generations of scientists. It would lead to some of the most profound ideas ever imagined, and to the very edge of what physics can describe. The next chapter of the story begins where Einstein's equations end at the point where space-time itself begins to break apart. By the middle of the 20th century, Newton's law and Einstein's geometry stood together as two great pillars of understanding. Each worked flawlessly in its domain. Newton's equations could predict the paths of spacecraft and the orbits of moons with stunning accuracy. Einstein's theory explained the bending of starlight, the slowing of time near massive bodies, and the expanding fabric of the cosmos. Yet between these two worlds, the everyday and the cosmic, there remained a silent question. The universe, as Einstein described it, was continuous. Space and time were smooth, unbroken, like a vast ocean with gentle waves. But quantum mechanics had shown that nature is not continuous at all. Energy comes in discrete amounts, and matter behaves like both wave and particle. Nothing in the microscopic world is perfectly smooth. This contradiction lay at the heart of modern physics. Einstein's theory of gravity treated the cosmos as a flowing fabric. Quantum theory treated it as a storm of uncertainty. Both could not be true in the same way. Somewhere, deep beneath the surface of known physics, one description must give way to the other, or both must merge into something new. To see the conflict, imagine compressing matter into a smaller and smaller region of space. According to quantum theory, particles jitter and fluctuate, unable to rest perfectly still. But according to general relativity, as mass becomes denser, it bends space-time more sharply. When this bending grows extreme enough, space-time collapses inward, forming a black hole. At the center of a black hole, Einstein's equations predict an impossible point, a singularity of infinite density, where space-time itself ceases to have meaning. Infinite curvature, infinite energy, infinite gravity, but infinities are signs of failure, not truth. They tell physicists that the mathematics has reached its limit. Inside a singularity, quantum effects should be enormous, yet Einstein's theory cannot describe them. Gravity there is so strong that even light cannot escape. Yet quantum mechanics insists that information can never be destroyed. Something deeper must reconcile these two principles. Physicists began to suspect that the smooth geometry of space-time must break down at unimaginably small scales. Perhaps below a length called the Planck scale, around 10 to the power of minus 35 meters, space and time themselves become granular, woven from a network of tiny quantum events. If that is true, then gravity might emerge from these microscopic patterns, just as waves emerge from the motion of countless molecules in water. Gravity might not be fundamental at all, but a reflection of something even smaller and stranger. For now, though, the surface view still holds. Einstein's universe of curved spacetime continues to describe the stars, the galaxies, and the dance of cosmic expansion. Its predictions remain unmatched in accuracy. When astronomers watched the merger of two black holes and detected ripples in space-time itself, gravitational waves traveling across the cosmos, they were hearing the direct echo of Einstein's geometry. But even that triumph raised new questions. If gravity can ripple, does that mean space-time itself can vibrate like a field? If so, might those vibrations come in quantized packets, like photons of light? And if they do, could we one day detect a single quantum of gravity, a graviton? Such thoughts mark the edge of known physics. Beyond that edge lies a landscape of possibilities: string theory, quantum gravity, and ideas that tie together space-time, information, and entropy. Yet even at the start of that frontier, one thing remains unchanged: the feeling that gravity is not fully understood. For all its precision, we still cannot say what gravity is. We can describe its behavior, its curvature, its waves. We can calculate how fast it travels, how it bends time, how it shapes galaxies. But we cannot yet say what it is made of. Is it a field, a particle, an emergent property, or a manifestation of something deeper than space-time itself? Perhaps gravity is not a substance at all, but a shadow cast by something more fundamental: the structure of information, or the statistical behavior of microscopic degrees of freedom we have not yet discovered. Perhaps it is a mirage of geometry that arises because we are creatures built from matter, perceiving motion through curved space-time. Every answer seems to open another question. Every equation points towards something just beyond reach. Gravity, the first invisible force humans ever recognized, remains the most mysterious of all. From Newton's falling apple to Einstein's bending space-time, we have come to see that the universe is not pulled by invisible threads, but shaped by the very nature of reality. And yet, that reality itself is incomplete. 2 centuries after Newton, Einstein tore away the veil that hid the mechanism of gravity. But his revolution also revealed the limits of our understanding. If gravity is geometry, then what is geometry made of? If space-time can bend, what gives it the ability to do so? What substance, if any, lies beneath the surface of the cosmos? These are not merely scientific questions, they are philosophical ones. They reach beyond equations into the heart of existence itself. For to know what gravity is made of is to ask what the universe is made of, and perhaps even what we are made of. The story of gravity is the story of human curiosity, of our refusal to accept the visible world as complete. It began with an apple falling toward the ground, but it leads to the very edge of time and space. And now, as we stand at that edge, a new vision of gravity begins to form, one that will rewrite the meaning of space, time, and the word force itself. The next chapter begins not with a fall, but with a curve, a bending of the universe that changes everything. At the dawn of the 20th century, the universe was still seen as a grand clockwork. Space was an empty arena where matter moved, and time was a river flowing evenly everywhere. Newton's laws had ruled for more than 200 years, unchallenged and triumphant. They had guided ships across oceans, traced the paths of comets, and predicted eclipses centuries in advance. But beneath that order, something felt incomplete. Newton's universe worked beautifully, but it did not explain why. It was Albert Einstein who first dared to imagine that perhaps the flaw lay not in the equations but in the stage itself. Perhaps space and time were not silent backdrops at all, but living participants in the drama of the cosmos. Einstein's first step toward this realization came in 1905, when he published his special theory of relativity. It revealed a universe where the speed of light was absolute, but space and time were relative, stretching and contracting depending on motion. Moving clocks ticked slower, distances shortened, mass increased with speed, and everything, no matter how it moved, was bound by one ultimate limit. Nothing could travel faster than light. For the first time, time itself became part of physics. No longer could scientists treat it as an invisible flow independent of space. Einstein showed that the two were connected, interwoven into a single fabric called space-time. But special relativity dealt only with motion in straight lines, without gravity. To include the pull of planets and stars, Einstein needed something more. For nearly a decade, he struggled with the problem. How could he describe gravity in a universe where space and time themselves were flexible? His key insight came from a simple thought experiment, the kind of imaginative leap that only Einstein could make. Picture a man falling freely from a rooftop. In that instant of falling, he feels weightless. Everything around him, from the tools in his hands to the dust in the air, falls alongside him at the same rate. For that moment, gravity seems to disappear. Now picture the same man inside a sealed elevator in deep space, far from any planet. If rockets push the elevator upward, he feels pressed against the floor, as if gravity had suddenly returned. Einstein realized that these two situations are identical in every measurable way. Falling in a gravitational field and accelerating in empty space produce the same sensation. This became the principle of equivalence, the seed of general relativity. If acceleration and gravity are indistinguishable, then gravity itself must be the effect of acceleration through curved spacetime. Then une for ting and crustation. Then une and crustish. Einstein began to see gravity not as a force, but as a feature of geometry. Matter and energy tell spacetime how to curve, and spacetime tells matter how to move. A planet orbiting a star does not feel a pull in the traditional sense. It simply moves along the curved path, defined by the star's mass. To explain this new vision mathematically, Einstein had to venture into a world of complex geometry, known as tensor calculus. He worked tirelessly, often alone, writing equations by hand, crossing them out, rewriting them again. His notebooks from those years are filled with the restless energy of a mind chasing truth. Finally, in 1915, he found the answer. His field equations described how the presence of mass and energy bends space-time, and how that curvature governs motion. The law of gravity was no longer a mysterious pull through emptiness. It was the shape of reality itself. The beauty of the idea was breathtaking. The sun does not drag planets through space with invisible strings. Instead, it shapes the space-time around it, and the planets simply follow the natural curves of that geometry. They are like marbles rolling along a distorted surface, moving not because they are pulled, but because the landscape itself bends beneath them. Even light, which has no mass, follows those curves. As it passes near a massive body, its path bends. The stronger the gravity, the sharper the bend. This prediction would soon become one of the most dramatic confirmations of Einstein's theory. In 1919, British astronomers led by Arthur Eddington observed stars near the edge of the sun during a total eclipse. The starlight had shifted position, exactly as Einstein had predicted. The world was astonished. Headlines declared that Newton's universe had been overturned. Einstein became a global figure. Overnight, the man who had redefined the very structure of the cosmos. Yet fame was never his goal. What mattered to him was the idea itself, the realization that space and time were not passive. They could warp, stretch, and even ripple. Gravity was no longer a force reaching across emptiness. It was the natural consequence of how space-time responds to matter. This was a profound shift in understanding. In Newton's world, the planets obeyed laws imposed from outside, like gears in a perfect machine. In Einstein's world, the laws arose from within, from the geometry of the universe itself. Space and time were no longer the stage, they were part of the play. General relativity was more than a scientific theory. It was a revolution in the way humans perceive existence. It told us that what we call gravity is not something that acts through space, but something that is space. It connected geometry, energy, and motion into one seamless whole. But the new vision also brought new puzzles. If space-time could bend, what did it mean for the nature of reality? Could space-time itself have structure? Could it vibrate or change? If a massive star were to move suddenly, would the distortion it creates ripple outward like waves on a pond? Einstein's equations said yes. They predicted the existence of gravitational waves, faint tremors in the geometry of the universe, spreading at the speed of light. Yet these waves were so weak that Einstein himself doubted they would ever be detected. Still, the idea was staggering. Gravity was not only curvature, it could move. The universe was not static, but dynamic, alive with motion and change. Space-time itself could carry energy, stretch, and contract. General relativity also revealed strange new cosmic possibilities. It allowed for regions of space where time slows to a near standstill, where light cannot escape, and where the curvature becomes infinite. These would later be known as black holes, perhaps the most dramatic prediction of Einstein's equations. At first, Einstein himself resisted the idea. The concept of a region so dense that even light is trapped seemed absurd. But over time, observations confirmed it. Nature had taken his equations at their word. The theory also predicted something even larger, that the universe could not remain static. Space itself must expand or contract, depending on how energy and matter are distributed. Einstein disliked this implication and added what he called a cosmological constant to keep the universe still. But later, when astronomers discovered that galaxies were indeed moving apart, he called that constant his greatest blunder. The fabric of space-time was not fixed. It was stretching, carrying galaxies with it, like leaves floating on a cosmic river. Einstein's revolution had reshaped our picture of the universe. Yet as precise as it was, General relativity still described a smooth, continuous cosmos. At everyday scales, this was perfect. But the deeper physicists looked into the quantum world, the less compatible it became. The world of atoms and subatomic particles operated by entirely different rules. There, energy came in discrete packets, and uncertainty ruled. Forces were carried by particles that exchanged quanta of energy. How could such a granular universe coexist with Einstein's smooth spacetime? For all its power, general relativity left one question unanswered. What happens when we try to describe gravity at the smallest possible scale? That question would lead to a new struggle, one that continues to this day. It is the attempt to unite the geometric universe of Einstein with the quantum universe of everything else. The next step in our story begins in that place of conflict, where the smoothness of space-time meets the jittering uncertainty of the quantum world and refuses to blend. The years following Einstein's discovery reshaped not only science but philosophy itself. The universe, once imagined as an orderly stage where objects move through absolute space and time, now became a living fabric, stretching and bending in response to energy and matter. The word gravity took on a new meaning. It was no longer a mysterious attraction, but the language of geometry written into the structure of existence. To understand how radical this was, imagine a massive star sitting in the middle of space. Around it, the invisible fabric of space-time curves, forming a valley. Any smaller object that comes near will follow the natural contours of that valley. It may orbit, spiral inward, or escape outward depending on its speed. No invisible hand tugs on it. The object is simply following the straightest possible path through curved space-time, called a geodesic. To us, that motion feels like a force, the pull of gravity. But Einstein showed that there is no pull at all. There is only geometry. The apple does not fall because the Earth attracts it, but because the Earth bends the space-time around it, guiding the apple along a curved path toward its surface. The feeling of weight is not a mysterious force pressing down. It is the resistance of the ground pushing up, preventing us from following our natural path through space-time. This understanding redefined every concept in physics. Even time itself was no longer universal. A clock on the surface of the Earth ticks more slowly than one on a mountaintop, because deeper in the gravitational field, space-time is more curved. This effect, though tiny, is real and measurable. Without accounting for it, the satellites that guide global positioning systems would drift miles off course each day. Einstein's theory transformed abstract mathematics into the rhythm of the cosmos. It described how light could bend around stars, how time could dilate near massive objects, and how entire galaxies could shape the expansion of the universe. It predicted black holes, gravitational lensing, and the birth of the cosmos itself in a fiery beginning billions of years ago. But the beauty of general relativity lies not only in its accuracy, but in its simplicity. The field equations are a balance between geometry and energy, a dialogue between matter and space-time. Mass tells space-time how to curve. Space-time tells mass how to move. That elegant reciprocity became one of the most profound relationships ever discovered. Still, Einstein's equations are not easy to solve. Only in a few special cases can they be expressed neatly. One of those cases describes the region around a single, perfectly spherical mass, the solution discovered by Karl Schwarzschild while serving at the front during the First World War. His calculation revealed something astonishing. If enough mass is packed into a small enough region, space-time curves so sharply that nothing, not even light, can escape. Thus was born the concept of the black hole. At first, no one believed such a thing could exist in reality. Even Einstein dismissed it as a mathematical curiosity. The idea that a star could collapse into a region where time itself stops was too extreme. Yet decades later, observations would prove otherwise. Astronomers found stars orbiting invisible companions and detected the energy from gas spiraling into unseen wells of gravity. The shadows of these cosmic abysses confirmed that Einstein's equations described not only what could exist, but what must exist. General relativity also predicted something subtler, that the motion of massive bodies should create ripples in space-time itself. When two stars orbit one another, they should stir the fabric of the universe like paddles in water, sending waves outward at the speed of light. These waves would be unimaginably faint, stretching and compressing space by less than the width of a proton. For most of the 20th century, they remained only a mathematical whisper. Then, a century after Einstein's discovery, the whisper became a sound. In the year 2015, the Laser Interferometer Gravitational Wave Observatory detected the first gravitational waves, the echo of two black holes colliding more than 1 billion light-years away. The signal matched Einstein's prediction with exquisite precision. The universe had finally spoken in the language of geometry, and humanity had learned to listen. This confirmation elevated general relativity from theory to fact. It was no longer just a model of how gravity might work. It was a description of how the universe truly behaves. Every ripple, every orbit, every stretch of time was evidence that space-time is real and dynamic. Yet the discovery also deepened the mystery. If space-time can ripple, does that mean it behaves like a field? And if it is a field, can it be quantized, broken into particles like photons of light? Could there be a particle that carries gravity, a graviton? This question struck at the core of physics. For electromagnetism, the photon is the messenger particle. For the strong nuclear force, gluons carry the binding energy between quarks. For the weak nuclear force, the W and Z bosons govern radioactive decay. Every known force has a carrier particle, except gravity. Einstein's theory, for all its majesty, has no place for such a particle. It treats space-time as a continuous surface, not a collection of quanta, but the quantum world refuses to be smooth. It demands discreteness, uncertainty, and probability. If space-time can ripple, then perhaps those ripples come in quanta, and if they do, then gravity must also have a particle description. Einstein himself resisted quantum theory. He admired its mathematical success, but doubted its completeness. God does not play dice with the universe, he once said. Yet experiment after experiment confirmed that the microscopic world truly does play dice, that uncertainty is built into the fabric of reality. As the 20th century progressed, physicists began to unify the other forces under the framework of quantum field theory. Electromagnetism merged with the weak nuclear force, and the strong force found its place in the theory of quarks and gluons. But gravity refused to fit. Every attempt to quantize it led to infinities, equations that collapsed into meaninglessness. The conflict was absolute. General relativity described the universe on the grandest scales: stars, galaxies, the curvature of the cosmos. Quantum theory described it on the smallest scales: atoms, particles, the fabric of matter itself. But between those two realms lay a chasm that neither could cross. At ordinary energies, this conflict does not matter. The equations of general relativity guide spacecraft flawlessly, while quantum theory governs the technology in every computer and smartphone. But near the extremes, near black hole singularities, or at the birth of the universe, both theories must operate at once. And there, they break. Where gravity becomes infinitely strong and space-time infinitely curved, quantum effects cannot be ignored. Yet when physicists try to calculate those effects, the numbers explode into infinities that make no sense. The two greatest theories in science, each so successful on its own, cancel each other out when combined. This is where the quest for a deeper truth begins, the search for a unified theory that can describe both the smooth geometry of space-time and the granular dance of the quantum world. It is a search that has driven physics for more than a century, leading to ideas both astonishing and speculative. From quantum gravity to string theory, from holographic principles to entropic forces, each attempt is a step toward reconciling Einstein's elegant curves with the flickering quanta beneath. But before those modern theories took shape, one idea emerged first, the simplest and most direct extension of quantum logic to gravity itself. If every force has a particle, then perhaps gravity does too. If light has photons, then maybe space-time has gravitons. And thus began a new chapter in humanity's understanding of the universe. A chapter where the smoothness of geometry met the graininess of quantum mechanics, and reality itself trembled under the weight of that contradiction. Einstein's vision had reshaped the very meaning of reality. Space and time were no longer the empty containers of existence. They were dynamic, responsive, and alive. Matter told space-time how to curve, and space-time told matter how to move. The universe had become a grand conversation between geometry and energy. Yet for all its beauty, general relativity was not the final word. It described the cosmic dance of planets, stars, and galaxies, but it struggled to whisper the language of the very small. Beneath the smooth fabric of space-time, something restless was stirring the strange world of quantum mechanics. By the early decades of the 20th century, new discoveries had shattered the idea that nature was continuous. The electron, once imagined as a simple particle, began to show both particle and wave behavior. Light, long known as a wave, began to behave like a stream of particles. Energy itself came in quanta, indivisible packets, whose interactions defied classical logic. Where Einstein saw a universe guided by geometric certainty, quantum physics revealed one governed by probability. The position of a particle could not be known exactly, only its likelihood. The act of measurement itself changed the outcome. Reality, it seemed, was not a solid structure, but a shimmering field of possibilities. At first, this did not seem to threaten Einstein's theory. Gravity was so weak, compared to other forces, that its quantum nature, if it existed, was invisible at ordinary scales. The curvature of space-time worked perfectly well for planets and stars, but when physicists looked deeper into the cores of atoms, or the first moments after the birth of the cosmos, they realized that the two pictures of the universe could not coexist. Einstein's space-time was smooth, continuous, and deterministic. Quantum mechanics was granular, uncertain, and discontinuous. Each worked perfectly within its own domain, but at their intersection, the realm of extreme gravity and infinitesimal scales both fell apart. Nowhere is this conflict more vivid than in the heart of a black hole. At its center, Einstein's equations predict a singularity, a point where curvature becomes infinite and time ceases to exist. But infinite values are not physical. They signal the breakdown of the theory itself. Quantum mechanics, meanwhile, insists that nothing can shrink into an infinitely small point. Energy fluctuates. Particles appear and vanish. Uncertainty rules. Something must give way. And yet, neither theory yields easily. Einstein's geometric description has been confirmed across the vastness of the cosmos, from the precession of Mercury's orbit to the ripples of gravitational waves. Quantum mechanics, in turn, has been proven in every experiment ever devised. Its accuracy, reaching 1 part in a billion. Both are true, and yet they contradict each other. The question is not which theory is wrong, but how they can both be right. What kind of universe allows two incompatible descriptions to govern it simultaneously? Could there be a deeper framework that unites them, a theory that explains both the bending of space-time and the jittering of quantum fields as two sides of the same coin? Einstein himself sought such a unification. For the rest of his life, he searched for equations that would merge gravity with electromagnetism, the only other known force at the time. But his search led him down lonely paths. The physics of his later years was elegant but sterile, unable to explain the new discoveries of quantum theory. He had glimpsed a deeper truth, but could not bridge the chasm between geometry and probability. Meanwhile, the next generation of physicists, Bohr, Heisenberg, Schrödinger, and Dirac, pushed quantum mechanics forward, exploring a world where energy fields replaced forces, and particles emerged as excitations within those fields. They found that electromagnetism could be perfectly described by the exchange of photons. The weak and strong nuclear forces could be expressed in similar terms. Every interaction had a carrier particle. Every field was quantized, except one. Gravity resisted. It refused to fit the pattern. When physicists tried to quantize Einstein's equations, the mathematics produced nonsensical infinities that no trick could tame. Space and time, the very stage on which all quantum events unfold, could not themselves be treated as actors within that framework. It was as if the universe had drawn a boundary, a line that no theory could yet cross. On one side lay the domain of the small, ruled by uncertainty and quantum fields. On the other lay the vast, curved geometry of space-time. Between them, a fog of ignorance. To move beyond that boundary, physicists began to imagine new ideas. Perhaps space-time itself was not continuous, but made of something deeper. Perhaps it could be built from quantum building blocks that, when combined, gave rise to the illusion of smoothness. Perhaps gravity, too, could have a messenger particle, a graviton, just as light has photons. These speculations marked the dawn of a new era in physics, one that sought to blend the geometry of Einstein with the granularity of the quantum world. Einstein's revolution had shown that gravity was not a force acting through space, but the shape of space itself. Yet this very insight demanded a further answer. If gravity is geometry, what shapes the geometry? If space-time bends, what gives it the power to bend? What are the quantum ingredients of reality that allow curvature to exist at all? The next chapter in our story takes us there, into the realm where the smoothness of space-time gives way to the graininess of the quantum world, where uncertainty reigns, and where the geometry of Einstein begins to crumble under the pressure of Planck-scale physics. In that strange domain, the rules of ordinary space and time no longer hold. The universe becomes a foam of possibilities, and the very question of what gravity is begins to take on a new and even deeper meaning. The 20th century was an age of divided truth. On one side stood Einstein's magnificent vision, a universe of smooth, curved space-time, where gravity was geometry, and geometry was law. On the other stood the strange new world of quantum mechanics, a universe that flickered and shimmered with uncertainty, built from invisible quanta that appeared and vanished in the blink of a thought. Both theories worked perfectly, each tested to exquisite precision, and yet, when placed side by side, they spoke different languages. To most of physics, this duality was tolerable. The quantum world ruled the very small atoms, molecules, and particles, while Einstein's relativity ruled the very large planets, stars, and galaxies. Their domains rarely overlapped. For decades, scientists could pretend the universe was divided into two realms that would never collide. But nature does not respect our divisions. There are places where the very large and the very small meet, where the rules of geometry and the rules of quanta must both apply. At those boundaries, the fabric of reality begins to fray. The first of these places lies at the heart of a black hole. According to general relativity, a collapsing star can squeeze itself into an infinitely small point, a singularity where curvature becomes infinite and time stops. But quantum mechanics refuses to accept infinities. It insists that uncertainty forbids such precision. Nothing in nature can be confined to a perfect point. The more tightly you try to compress matter, the more violently its quantum energy resists. Somewhere, the two descriptions must clash. The second place is the beginning of time itself, the moment of the Big Bang. If the universe once existed in a single dense state, then general relativity predicts infinite curvature there too. But again, quantum mechanics forbids it. The early universe must have been a storm of fluctuations, a quantum haze where the very concept of space and time breaks down. In both cases, Einstein's smooth geometry collapses under quantum pressure. The elegant curves of space-time give way to something wild and granular, a universe in which geometry itself becomes uncertain. To understand why the conflict runs so deep, we must look closely at what quantum theory says about reality. It begins with the idea that energy and matter are not continuous substances but excitations of invisible fields that fill all of space. Every type of particle, electron, photon, quark, is a vibration in its own field. These fields are not limited to matter. They are the foundation of every force in nature. The electromagnetic force, for example, is carried by the photon, a massless particle that mediates the exchange of energy between charged particles. The strong nuclear force that binds protons and neutrons is carried by gluons. The weak force that governs radioactive decay is carried by W and Z bosons. In each case, the force emerges from the quantum interactions of these messenger particles. This framework, quantum field theory, describes the universe as a symphony of interacting vibrations. Each particle is a note, each field an instrument, and together they form the music of existence. But when physicists tried to apply this same idea to gravity, the harmony shattered. Einstein's equations treat gravity not as a force but as the shape of space-time itself. In quantum field theory, every field exists within space-time, but gravity is space-time. To quantize it would mean turning the very stage of the universe into a participant, allowing it to fluctuate and vibrate like any other field. At first glance, this might seem straightforward. If electromagnetism has photons, then gravity should have its own messenger, a particle called the graviton. It would be massless, like the photon, and carry a spin of 2 rather than 1. Mathematically, such a particle can exist. In weak gravitational fields like those far from stars and planets, a graviton-based theory of quantum gravity even works beautifully. But when the gravitational field grows strong, the equations explode. The problem lies in the way gravity couples to itself. Unlike electromagnetism, where charges can cancel each other out, gravity only attracts. Every quantum of energy, including the energy of the gravitational field itself, adds more gravity. The result is a cascade of infinite feedback. Each calculation spawns more infinities than can be renormalized, the process physicists use to remove meaningless infinite values from their equations. In simpler terms, quantum gravity refuses to behave. The mathematics of curvature does not bend easily into the mathematics of probability. The two frameworks resist merging, as if the universe itself is telling us that they are incomplete on their own. Physicists call this the problem of non-renormalizability. It means that when gravity is treated as just another quantum field, the resulting infinities cannot be absorbed or ignored. They destroy the predictive power of the theory. At ordinary scales, this is irrelevant. The gravitational force between two atoms is so unimaginably weak that it can be ignored. But near black holes, or at the first moments after the Big Bang, those infinities cannot be dismissed. To move forward, science must somehow reconcile the continuous curves of Einstein with the discrete quanta of the microscopic world. It must find a theory that describes gravity not as a smooth geometry, but as something that emerges from the quantum realm. The challenge is immense. Einstein's equations work perfectly when describing planets or galaxies, while quantum field theory works perfectly for subatomic particles. But when you combine the two, neither works at all. The failure is not one of calculation, but of concept. Relativity assumes that space-time is smooth and continuous, that every point has meaning. Quantum theory assumes that nothing can be known exactly, that uncertainty is woven into every measurement. One says geometry is reality. The other says reality is probability. When we try to unite them, we find that space and time themselves may not be what they seem. Perhaps they are not fundamental at all. Perhaps the smooth space-time of Einstein's universe is only an approximation, a large-scale illusion that emerges from something deeper, something granular and quantum beneath. As the 20th century turned toward its close, a new generation of physicists began to ask the question in a different way. Instead of asking how to quantize gravity, they asked what gravity is. What if the fabric of space-time is not continuous but woven from quantum threads? What if the smooth geometry of Einstein's equations is a kind of average behavior, like the calm surface of a sea that hides a turbulent chaos beneath? These questions opened a door to new ideas and to a new search for gravity's hidden nature. To enter that door is to leave behind the familiar world of geometry and enter a domain where space-time itself becomes uncertain, where particles may be vibrations of something smaller, and where the universe may be built not from matter or energy, but from information. But before any of that could be imagined, physicists had to face one unavoidable truth. If gravity is a quantum phenomenon, then it must have a particle. It must have a carrier of its own, a whisper that moves through the fabric of existence. And so, the hunt for that particle began a search for the graviton, the elusive messenger of gravity, the final missing piece of nature's puzzle. The idea of the graviton was born not from observation, but from necessity. The quantum world demands that every force be mediated by something, a carrier that transfers energy and momentum between particles. Electromagnetic forces flow through photons. The strong nuclear force relies on gluons. The weak nuclear force uses the W and Z bosons. Each of these carriers arises naturally when the corresponding field is quantized, breaking down into discrete packets of interaction. Gravity, if it is truly a force, must follow the same rule. Somewhere, hidden deep within the mathematics of space-time, there must exist a particle that transmits its influence, a graviton. Physicists began to imagine what such a particle would be like. It would have no mass, because gravity acts across infinite distances without fading completely. It would carry a spin of 2, distinguishing it from the photon's spin of 1, and giving it the unique ability to curve space-time rather than simply push or pull. It would move at the speed of light, whispering geometry from one point of the universe to another. But the graviton would also be unimaginably weak. To feel the gravitational pull of a single quantum of gravity, one would need detectors larger than planets and patience longer than the age of the cosmos. The effect of one graviton is so small that no conceivable experiment could detect it directly. It is like trying to measure the motion of a single molecule in a hurricane. Yet even if we cannot detect it, the concept matters. The graviton serves as a bridge, a way to translate Einstein's continuous curvature into the discrete language of quantum mechanics. If space-time can ripple, then those ripples must come in quanta. Just as light waves are composed of photons, gravitational waves must, in theory, be composed of gravitons. At low energies and weak fields, this idea works beautifully. The mathematics of a massless spin-2 particle produces equations that look exactly like the weak field limit of general relativity. The geometry of space-time, in other words, emerges naturally from the behavior of countless virtual gravitons interacting in the quantum vacuum. But the harmony breaks when the fields grow strong. The infinities return, tearing the equations apart. Unlike photons, which ignore their own electromagnetic field, gravitons interact with one another, creating feedback loops that explode into unmanageable complexity. Each graviton carries energy, and energy itself produces gravity, which creates more gravitons in turn. The result is a runaway system that no known method can tame. This self-interaction problem lies at the heart of quantum gravity. Every attempt to calculate gravitational effects at high energies leads to infinite results that cannot be renormalized. That is, they cannot be made finite by adjusting a few parameters, as physicists do in quantum electrodynamics or the Standard Model. Gravity refuses to cooperate. To understand why this happens, imagine trying to describe the ocean by measuring each molecule of water. The sheer number of interactions makes the task impossible. In the same way, the gravitational field at the quantum level involves a web of self-interacting particles so dense and complex that the mathematics drowns in its own detail. For decades, this failure stood as a wall in physics. General relativity described the large, quantum theory described the small, but no single theory could describe both. Still, The graviton remained an alluring idea, a symbol of the unity scientists hoped to find. It represented the dream that all forces could be explained within one framework, that gravity too might emerge from the same quantum logic that governs the rest of nature. The search for a quantum theory of gravity soon gave rise to other, deeper questions. If the graviton exists, then space-time itself must be a kind of field. And if space-time is a field, then it should have its own energy, its own fluctuations, and its own uncertainty. The vacuum between stars should not be truly empty, but alive with invisible motion, a sea of virtual particles flickering in and out of existence, including perhaps virtual gravitons. Quantum theory predicts this restless vacuum. Even in perfect emptiness, energy cannot be zero. Instead, it fluctuates constantly, creating pairs of particles and antiparticles that appear, interact, and vanish in unimaginably short timescales. This constant boiling of existence is called the quantum vacuum. If gravity arises from that vacuum, then space-time itself may be nothing more than a large-scale pattern emerging from those microscopic fluctuations. The smooth geometry of Einstein's equations could be the average behavior of countless quantum events beneath the surface, just as temperature is the average motion of countless atoms. But no one yet knows how to describe that microscopic structure. Attempts to merge gravity with quantum mechanics have spawned entire new fields of research, from loop quantum gravity, which tries to quantize space itself, to string theory, which replaces point-like particles with tiny vibrating strings whose resonances create both matter and force. At the center of these efforts lies a single question: is gravity fundamental, or is it emergent? Does it exist as a basic property of nature, or does it arise from something deeper, something that hides beneath the surface of space-time? Einstein's equations are elegant but silent on this point. They tell us how curvature behaves, but not what curvature is. If space-time bends, what substance allows it to do so? What gives geometry its flexibility? What is the fabric of the universe made from? The graviton offers one possible answer: a quantum of the gravitational field, the smallest possible ripple in space-time. But if that is true, then space-time is not continuous. It must be quantized, woven from discrete pieces that combine to form the illusion of smoothness. This would mean that the most basic elements of reality are not points in space, but relationships between them, networks of information connecting quantum events. The geometry we perceive would be only the large-scale shadow of those relationships. Such ideas sound abstract, but they carry profound implications. If gravity is emergent, then space-time itself may not be fundamental. The universe might be built not from matter or energy, but from the correlations between them from information. In that vision, gravity is not something to be added to quantum mechanics, but something that comes out of it. The curve of space-time would be a collective behavior, like the pressure of air or the temperature of water, not fundamental, but statistical, arising from the behavior of countless unseen components. This notion is radical. It shifts gravity from being one of nature's building blocks to being one of its consequences. But it also offers hope. Because if gravity is emergent, then the unification of quantum mechanics and relativity may not require forcing two incompatible frameworks together, but realizing that one emerges naturally from the other. Still, the graviton remains the simplest symbol of that dream, a single, invisible messenger particle, carrying the geometry of the cosmos, connecting the quantum and the cosmic realms. The search for it continues not because we expect to catch one, but because the pursuit itself leads us closer to the foundations of reality. But before we can know if gravity truly emerges from deeper laws, we must face the failure that started it all, the mathematical breakdown of Einstein's and Planck's worlds at the smallest scales. There, near the Planck length of 10 to the power of -35 meters, the equations of both relativity and quantum mechanics collapse into paradox. At that scale, space and time cease to be meaningful. The very fabric of the universe dissolves into a storm of fluctuations so violent that geometry itself loses definition. It is in that chaos that the next frontier begins. At first glance, space-time seems perfectly smooth. We move through it effortlessly, measuring distances with rulers and ticking seconds with clocks, believing that between any 2 points lies an unbroken line. But this smoothness is an illusion born of scale. Much like the calm surface of the sea hides the restless churning beneath. As we dive deeper into smaller and smaller realms, the very structure of reality begins to tremble. Physicists measure this descent not in meters, but in orders of magnitude. A human hair is roughly 1/100th of a centimeter wide. An atom is 10,000 times smaller than that. Its nucleus, where protons and neutrons reside, is yet another 100,000 times smaller. Beyond that, the building blocks of those particles, quarks, are smaller still, so small that no experiment has ever measured their true size. And far below even that lies the Planck length, around 10 to the power of minus 35 meters, a scale so tiny that if an atom were expanded to the size of the observable universe, the Planck length would still be smaller than a single grain of sand within it. At this unimaginable scale, our current understanding of physics breaks apart. The equations of general relativity and quantum mechanics, which have guided us so reliably through every other domain, begin to produce nonsense. Space-time itself becomes uncertain. The concept of a point loses meaning. Imagine zooming in on a patch of empty space, magnifying it beyond all limits. At first, it looks perfectly still, but as you approach the Planck scale, emptiness begins to shimmer. Energy fluctuates violently, creating miniature distortions in space-time, tiny hills and valleys that rise and collapse in trillionths of a trillionth of a second. This restless chaos is known as quantum foam. It is the sea beneath reality's surface, the storm of creation and annihilation that underlies everything. In this frothing chaos, black holes, smaller than subatomic particles, may form and vanish in the blink of an eye. Wormholes may flicker open and close before light itself could cross them. The smooth geometry of Einstein's equations dissolves into a storm of quantum uncertainty. No experiment can yet reach such scales, but the mathematics points clearly toward this conclusion. Space-time cannot remain continuous all the way down. The quantum world refuses to curve smoothly. It rebels against the calm order of relativity, demanding a universe built from fluctuations rather than from forms. Physicists call this the breakdown of classical geometry. It means that at the smallest scales, the very notions of distance and duration cease to exist. There is no before or after in the conventional sense, no well-defined coordinates, no stable background against which events unfold. Instead, everything becomes probabilistic. The shape of space-time itself becomes a wave of possibilities. Some theorists describe this as the foam of creation, the dynamic medium from which the universe continually renews itself. Others see it as a clue that space-time may be emergent, that the geometry we experience is only an average of the quantum chaos below. In either case, the message is clear. The smooth curves of Einstein's universe are not fundamental. They are the large-scale behavior of something far more intricate and restless beneath. At the Planck scale, gravity and quantum mechanics collide in full force. The gravitational pull of even a tiny amount of energy becomes enormous because energy itself creates curvature. But the uncertainty principle of quantum mechanics ensures that energy cannot be precisely defined within a small region. The smaller the region, the greater the energy fluctuations, and the stronger the gravitational distortions they produce. Eventually, these fluctuations become so intense that they warp space-time beyond recognition. The geometry twists in upon itself, forming transient micro-black holes that appear and vanish constantly. The vacuum is no longer empty. It is alive, seething with temporary structures that blink in and out of existence. At this depth, the familiar laws of physics no longer apply. The separation between space and time blurs. Cause and effect lose their meaning. even the concept of dimension becomes uncertain. Some regions may temporarily behave as if the universe has fewer dimensions than 4, while others may momentarily host more. Here, gravity is no longer a smooth curvature, but a wild, fluctuating field, a network of quantum events, continually rewriting its own geometry. If gravitons exist, they are born and destroyed here, exchanging energy faster than any clock could measure. The universe at this scale is not a fabric, but a storm, and we have only begun to imagine its true nature. This is the frontier where theories such as string theory and loop quantum gravity attempt to venture. They propose that what we call space-time is not a continuous sheet, but a network of discrete elements or vibrating strings, bound together by mathematical consistency. In these models, the Planck scale is not a wall but a window, a glimpse into the machinery of the cosmos. But no one yet knows which, if any, of these ideas is right. The energies required to probe the Planck scale are so immense that no experiment on Earth can reach them. The Large Hadron Collider, humanity's greatest particle accelerator, can reach energies of around 10 to the power of 13 electron volts, still more than 20 orders of magnitude too weak. To directly explore the Planck realm, we would need a collider the size of the Milky Way, and so we are left with mathematics, observation, and imagination. We look for indirect clues in the behavior of black holes, in the relic light from the early universe, in the subtle patterns of gravitational waves that ripple through space-time. Each of these may carry whispers from the quantum foam, faint hints of the realm where geometry dissolves. What we know for certain is that gravity cannot remain purely geometric. The smooth curvature of Einstein's universe is only an approximation, a magnificent, elegant description that begins to fail, where quantum uncertainty grows too fierce. At those scales, we glimpse the need for something deeper, a theory that does not simply curve space-time, but explains how space-time itself arises. A theory that unites geometry and probability, continuity and discreteness, curvature and quanta. And so the story of gravity turns once more. We began with Newton, who saw an invisible force acting across emptiness. Einstein replaced that force with geometry, revealing that mass and energy shape the stage itself. But now, at the edge of knowledge, we face a new possibility, that even geometry is not fundamental. That beneath the curves of space-time lies a restless quantum sea, whose ripples give rise to all that we call reality. The next step in this journey takes us into the heart of that possibility, the search for the graviton, the elusive quantum of gravity, the smallest possible ripple in the fabric of existence. If it exists, it could bridge the gap between Einstein's curved universe and the quantum world that refuses to bend. It is the ghost particle of space-time itself, and finding it could reveal what gravity is truly made of. Imagine the universe as a vast ocean of invisible waves. Every vibration, every interaction, every glimmer of light is a ripple in that sea. Photons are the ripples of the electromagnetic field. Gluons are the waves that bind quarks within the heart of atoms. W and Z bosons carry the weak force that turns one kind of particle into another. Each force of nature is a song, and each song is carried by its own note, a particle that embodies its essence. If this is true for all other forces, then gravity must have its own note too, its own messenger, its own quantum. Somewhere, hidden in the trembling structure of space-time, there must exist a particle that carries the whispers of curvature itself, the graviton. To imagine such a particle is to stand on the bridge between two worlds, Einstein's geometric cosmos and the quantum sea beneath it. In the language of quantum field theory, every force arises from the exchange of particles. When two electrons repel one another, they are trading photons back and forth. When quarks bind together inside a proton, they exchange gluons. But in gravity, there is no known messenger, no exchange particle we can see or measure. And yet, if quantum mechanics is universal, gravity must obey it too. The graviton, in theory, is massless, because gravity reaches across infinite distances. It moves at the speed of light, carrying the geometry of space-time from one region to another. It has a spin of 2, meaning that it influences not just direction or energy, but the very shape of motion itself. Unlike the photon, which can push or pull depending on electric charge, the graviton always attracts. It curves everything toward everything else, uniting all matter under its influence. The idea of the graviton was first formalized in the early 20th century, when physicists began applying quantum principles to every known force. The logic was simple. If gravity causes waves, and if all waves are quantized, then there must exist quanta of gravity. Those quanta are the gravitons, the smallest possible ripples in the fabric of space-time. In weak gravitational fields, where the curvature of space-time is gentle, this idea works astonishingly well. The equations describing a field of massless spin 2 particles produce results nearly identical to Einstein's theory in those conditions. It is as if the smooth geometry of general relativity emerges naturally from the combined behavior of countless gravitons interacting through quantum rules. But as the field grows stronger, the mathematics collapses. The same feedback loops that plague every attempt to merge quantum mechanics with gravity reappear. Every graviton interacts not just with matter, but with every other graviton, because each carries energy, and energy itself creates gravity. It is a self-coupling problem that spirals toward infinity. This makes the graviton both elegant and tragic, a beautiful theory that cannot yet describe itself. Even so, the idea continues to guide the search for a unified understanding of nature. To see why, it helps to remember that all other forces once seemed mysterious until their mediating particles were discovered. Before the photon was known, electricity and magnetism were treated as separate phenomena. Before gluons were understood, the strong force that binds protons together was a puzzle. Once those particles were revealed, the forces they carried made sense. The hope is that gravity, too, will one day yield to this pattern. Yet the graviton is not like other particles. It cannot be isolated, contained, or even detected in any direct way. The gravitational force it carries is unimaginably weak compared to the others. 2 protons, for example, attract each other gravitationally, but their electric repulsion is stronger by a factor of roughly 10 to the power of 36. The only reason gravity dominates at cosmic scales is because it always attracts, it never cancels itself out. But that same persistence makes it impossible to measure at the level of individual particles. To detect a single graviton, one would need an instrument sensitive enough to register the tiniest possible change in curvature. An instrument so large and so isolated that it would collapse under its own gravity before it could ever make the measurement. The universe itself conspires against us. This is why physicists often say that a direct detection of the graviton may be forever impossible. The act of measuring one would require more energy than the particle itself carries. It is the ultimate paradox, a phenomenon that must exist if quantum theory is universal, and yet one that nature hides so well, it may never be found. Still, there are indirect ways to search for its fingerprints. Every gravitational wave detected by observatories like the Laser Interferometer Gravitational Wave Observatory, the faint stretching and squeezing of spacetime caused by colliding black holes is, in principle, made of countless gravitons moving together. Just as a beam of light is composed of many photons, a gravitational wave would be a collective motion of these quanta. But there is a key difference. The energy of a single graviton is so minuscule that even the most violent cosmic events, the collision of entire galaxies, or the merging of supermassive black holes, would emit waves composed of quadrillions upon quadrillions to them. The combined effect can be detected, but the individual quanta remain far below the threshold of any conceivable measurement. The graviton, then, is not just elusive, it is practically invisible by definition. It is the faintest possible shimmer in the most delicate fabric imaginable. Yet the very existence of that fabric is the foundation of all reality. Without it, there would be no structure, no motion, no meaning to the concept of here or there. Gravity is not merely a force among others. It is the architecture of existence. And if the graviton exists, then that architecture has a quantum foundation, an atomic structure to space-time itself. This idea leads to an extraordinary possibility. If space-time is built from gravitons, then the universe we experience as continuous and smooth is actually granular at the deepest level, composed of countless microscopic interactions. The geometry we see may be a kind of average, a large-scale harmony arising from the vibrations of these invisible quanta. If that is true, then every moment of motion, every orbit of a planet, every bending of light near a star is, in essence, a song of countless gravitons moving together, shaping the universe note by note. But how can we ever prove such a thing? How can we reach across scales so vast from the smooth curves of galaxies to the subatomic tremors of space-time and find the link between them? The challenge of uniting these two pictures has driven physics for a century. It is a journey not just towards smaller scales, but toward deeper understanding, the realization that reality itself may be woven from the threads of information carried by the faintest of all particles. And so, the story continues. The search for the graviton is not merely a hunt for a particle. It is a quest to see whether geometry can become quantum, whether the universe's smooth surface hides a microscopic rhythm too small for us to hear. The graviton is the ghost of gravity, the whisper of curvature, the echo of the cosmos, trying to speak the language of quanta. And to follow that whisper, physics must go beyond the equations of Einstein, beyond the limitations of the standard model, and into the realm where space-time itself might not be what it seems. The search for the graviton is not just a search for a particle. It is a search for meaning, a way to understand whether space-time itself is fundamental or an illusion born of deeper laws. Every equation that describes gravity, every attempt to merge it with quantum mechanics, is a step into that mystery. In the language of quantum field theory, every force is described by a field that fills all of space, even in complete emptiness. Particles are simply the smallest excitations of those fields. A photon is a vibration in the electromagnetic field. A graviton, if it exists, would be the smallest vibration in the gravitational field, or, more precisely, in the geometry of space-time itself. To create such a theory, physicists tried to write down an equation for a massless spin-2 particle, the simplest mathematical object that could produce the effects of gravity. The first versions seemed to work. In weak gravitational fields far from stars or black holes, these equations behaved almost identically to Einstein's general relativity. The exchange of virtual gravitons between particles reproduced the familiar attraction we call gravity. It was a triumph of mathematical symmetry, but as the calculations deepened, the triumph began to unravel. The moment physicists tried to apply the same equations to stronger gravitational fields or to smaller scales, the mathematics erupted into infinities. When two gravitons interact, each one contributes to the energy of the gravitational field, which in turn generates more gravitons, which then interact again, endlessly. Every level of calculation produced new infinities, more divergent terms, and no consistent way to make them finite. Other forces could be tamed by a process called renormalization, a mathematical technique that allows physicists to absorb the infinities into measurable constants like charge or mass. But gravity resisted every attempt. Its self-interacting nature made it non-renormalizable. No finite number of corrections could make the equations stable. Each term spawned new ones, stretching out to infinity. This failure was not just technical, it was conceptual. It revealed that gravity behaves differently from all other forces. Where electromagnetism, the strong force, and the weak force are confined within space-time, gravity defines space-time itself. The stage cannot be quantized in the same way as the actors that move upon it. It was as though nature had drawn a line between two kinds of truth, the truth of geometry and the truth of probability, and refused to let them overlap. Physicists began to realize that something deeper must be missing. Perhaps the problem lay in our assumption that space-time is a smooth, continuous fabric. Perhaps it is not the stage of the play, but one of the characters, a dynamic system built from smaller constituents. At this point, the graviton became more than a hypothetical particle. It became a window into a new way of thinking. If space-time is made of quantum pieces, then those pieces must interact according to rules that give rise, at large scales, to Einstein's smooth geometry. The graviton would be the smallest unit of that structure, the quantum heartbeat of space-time. But if that is true, then the universe at the Planck scale at distances around 10 to the power of minus 35 meters must look nothing like the universe we know. The calm curves of relativity would dissolve into a storm of fluctuations, where space, time, and gravity themselves are uncertain. At such scales, quantum effects would dominate. Virtual particles would appear and vanish in fractions of a moment, dragging space-time along with them. Black holes smaller than atoms might form and evaporate almost instantly. The vacuum would become a living foam, full of transient geometries. In this view, gravitons would be like the bubbles in that foam, the smallest possible disturbances, flickering into existence as space-time itself vibrates. The question then becomes, what are those vibrations made of? If gravitons exist, what is the medium they ripple through? Einstein's equations say that space-time can bend, but they do not tell us what space-time is. Quantum theory insists that everything must have some underlying substance or field, but the gravitational field is unique. It is both the medium and the message. This circularity, where gravity shapes the geometry it moves through, makes quantization almost impossible. Every attempt to describe gravity as a field within space-time leads back to the same contradiction. Gravity is the structure of space-time itself. To break free from this loop, physicists began to imagine that space-time might not be fundamental. Perhaps it emerges from something deeper, something that behaves like a network of quantum relationships rather than a continuous fabric. One of the first ideas to take this seriously was loop quantum gravity, which proposes that space itself is composed of tiny loops, each representing a discrete unit of area or volume. In this framework, space-time is a lattice of quantum links, constantly fluctuating and rearranging. Geometry arises not from smooth curvature, but from the interconnection of countless microscopic loops. Another, even more radical idea was string theory. It began as an attempt to describe the strong nuclear force, but soon revealed something unexpected. In the equations of string theory, one of the vibration modes of a tiny one-dimensional string behaves exactly like a massless spin-2 particle, a graviton. It appeared naturally, not by design, but as a mathematical necessity. That discovery changed everything. Suddenly, gravity was not a separate force at all, but an inevitable feature of a theory that sought to unify all particles and forces as different vibrations of the same underlying entity. In string theory, the graviton is not a point-like particle but a specific mode of vibration, the way a string oscillates when it carries no mass, but influences the geometry of space-time around it. In that sense, gravity is built into the structure of the theory itself. But this solution came with a cost. To remain consistent, string theory requires additional dimensions beyond the familiar 3 of space and 1 of time. The equations demand 10 or even 11 dimensions, most of them curled up so tightly that we cannot see them. These hidden dimensions give gravity the room it needs to exist without collapsing into infinities. They allow the graviton to move freely in ways that our limited 3-dimensional intuition cannot imagine. Still, even with this elegance, string theory remains untested. Its predictions lie far beyond the reach of current experiments. Yet it offers something no other theory has achieved: a framework in which gravity arises naturally from quantum principles, rather than fighting against them. For now, the graviton remains a symbol, a particle we cannot detect, but must believe in if our understanding of nature is to remain whole. It represents the idea that space-time is not the end of the story, that there is another layer beneath the surface. Every step toward understanding the graviton brings us closer to a deeper vision of reality, one in which geometry, matter, energy, and information are all aspects of the same fundamental truth. It is a truth that whispers through the equations of relativity and the mathematics of quantum theory alike. A truth that suggests the universe may not be built from things, but from relationships, from the interplay of energy and information that gives rise to everything we perceive. And in that interplay, gravity is the voice that binds it all together, the gentle curve of existence, the echo of every motion, the rhythm of the cosmos itself. The next step in this journey will take us beyond the graviton into the clash between Einstein's continuous geometry and the discrete quanta that make up reality, where both theories break down entirely and new ideas must emerge from the ruins. The graviton, if it exists, is the most delicate of all particles, a ghost woven into the fabric of reality itself. It would have no color, no charge, no mass, no tangible presence. And yet, through it, every planet moves, every star forms, every galaxy holds its shape. It would be the faintest note in the cosmic orchestra, and without it, there would be no song. But for all its elegance, the graviton remains a mathematical dream. No experiment has ever revealed it, and perhaps none ever will. The energy required to create or detect a single graviton is so far beyond human reach that it borders on the impossible. The universe hides its quantum structure behind scales so small and energies so vast that we can only infer its existence indirectly. Yet the search continues, because the idea of the graviton points towards something profound, the need for a single, coherent description of nature. Einstein's curved spacetime explains the motion of planets and the expansion of the universe, but it cannot describe what happens inside an atom. Quantum field theory explains atoms, molecules, and the forces that bind them, but it cannot describe what happens when gravity becomes strong. Somewhere, both must be true at once. Somewhere they must meet. Physicists call this place the Planck scale, named after Max Planck, the German scientist who first uncovered the quantum nature of energy. It is a realm defined by numbers, so extreme they defy imagination. The Planck length, about 10 to the power of minus 35 meters, marks the smallest possible distance that can have meaning. The Planck time, about 10 to the power of minus 44 seconds, is the smallest measurable moment. And the Planck energy, roughly 10 to the power of 19 billion electron volts, is the energy at which gravity and quantum mechanics must merge. At those scales, space-time ceases to be smooth. The geometry that Einstein described begins to flicker, warp, and dissolve into quantum chaos. The gravitational field becomes a storm of fluctuations, its quanta appearing and vanishing faster than any light signal could trace. Gravitons, if they exist, swarm in countless numbers, constantly interacting, creating and annihilating each other in a self-sustaining turbulence. Here, the equations of physics fail completely. General relativity predicts infinite curvature, while quantum theory predicts infinite uncertainty. Together, they yield only paradox. Space-time becomes both infinitely curved and infinitely uncertain, both continuous and discrete. The result is neither geometry nor probability, but something we do not yet have the words to describe. This breakdown reveals the limits of our understanding. Einstein's theory cannot be the whole story. It works perfectly at human and cosmic scales, but falls apart at the smallest. Quantum theory, too, cannot be complete. It describes the behavior of particles and forces within space-time, but cannot explain where space-time itself comes from. Both are fragments of a larger truth we have not yet grasped. The graviton sits at the center of that mystery. It is the point where geometry and quantum theory collide, where the smooth meets the granular, where curvature becomes probability. But the very equations that predict its existence also show why it may be forever beyond reach. If you try to probe space-time at distances smaller than the Planck length, the energy required becomes so enormous that it creates a tiny black hole, swallowing the region you hope to observe. Nature protects its smallest secrets by hiding them behind the event horizons of its own creation. The closer we look, the less we see. This is not a failure of mathematics, but a warning, a sign that our concepts of space and time may not apply beyond a certain limit. The universe may not allow itself to be divided infinitely. There may be a smallest grain of geometry, a minimum scale of existence. If that is true, then the graviton is not merely a particle, but a clue to a deeper reality, one where space-time is built from discrete pieces, each interacting with the others through rules that give rise, at large scales, to the curvature we call gravity. In this view, Einstein's smooth universe is an approximation, like the fluid surface of water seen from afar. Up close, that surface breaks into droplets, each a tiny quantum of motion. The challenge is to find the theory that describes those droplets, the quanta of space-time itself. Over the years, physicists have followed many paths in search of this theory. Some have tried to refine the mathematics of quantum field theory, finding new ways to handle the infinities that plague it. Others have turned to more radical ideas, like loop quantum gravity, where space is woven from microscopic links that form a quantum network. And others still have looked to string theory, where the graviton arises naturally as a vibration of a tiny one-dimensional string. In string theory, gravity is not something added to the universe, but something inevitable. Every string, no matter how it vibrates, produces particles of different masses and spins. Among them, one particular vibration always behaves like a massless spin 2 particle, the graviton. It appears automatically, as though the universe itself cannot exist without it. This is perhaps the most compelling success of string theory. It unites gravity and quantum mechanics, not by forcing them together, but by revealing that both emerge from a deeper principle, the vibrations of strings in a higher dimensional space. In this picture, space-time itself is not fundamental, but a product of those vibrations. But this elegance comes at a price. String theory requires not just 4 dimensions, but 10 or 11. It predicts an enormous landscape of possible universes, each with its own geometry and physical laws. Our universe may be only one among trillions, a bubble in a higher dimensional sea. Still, the graviton remains the thread that connects them all, the common feature that links every version of string theory to the familiar universe we inhabit. It is the bridge between the quantum and the cosmic, between vibration and curvature. And yet, despite its power, even string theory has not solved the full mystery. It shows that gravity can arise from quantum principles, but it does not yet explain why. What is it about information, energy, and geometry that causes the universe to curve? Why does mass tell space-time how to bend? Why does curvature tell mass how to move? These questions linger like echoes at the edge of understanding. In the end, the graviton remains what it has always been: an idea, a whisper, a hint that the universe is more interconnected than we can yet comprehend. It is the shadow of the unseen, the particle that carries not just a force but the structure of existence itself. Its pursuit has led us to the brink of new physics, to theories that extend beyond space and time as we know them. But those theories, elegant as they are, also hint at something stranger still: that gravity might not be a fundamental force at all, that it might arise from deeper laws governing information and entropy, from the quantum fabric of the universe itself. To follow that idea, we must take another leap beyond geometry, beyond particles, into a realm where gravity is not a thing, but an emergent phenomenon, born from the hidden patterns of information that underlie reality. That is where our journey leads next, to the collision of theories, to the failure of old ideas, and to the birth of new ones. The history of physics is a story of unity. Again and again, discoveries that once seemed separate were revealed to be connected. Electricity and magnetism became one. Light was shown to be a wave of that same electromagnetic field. The weak and electromagnetic forces, once thought distinct, turned out to share a single origin. Every great leap in science has been a step toward deeper simplicity, a realization that the universe speaks one language, written in many dialects. But gravity refuses to join the conversation. It stands apart, proud, and silent, obeying its own laws. It shapes the universe on the largest scales, yet it does not fit within the same framework that governs everything else. For a century, physicists have tried to bring Einstein's curved spacetime into harmony with the quantum world, and every attempt has failed. The problem is not one of misunderstanding, but of contradiction. General relativity describes gravity as the curvature of spacetime, a smooth and continuous fabric that bends in response to energy and mass. Quantum mechanics, by contrast, describes the universe as granular and uncertain, built from discrete particles and fluctuating fields. Each theory is perfect in its own realm, relativity in the cosmic, quantum mechanics in the microscopic. But where they meet, their rules destroy one another. At ordinary scales, this conflict is invisible. A satellite orbiting Earth follows Einstein's equations to extraordinary precision, while the atoms inside it obey quantum laws with equal perfection. The two realms coexist peacefully, never interfering. But at extreme scales near black holes, or at the birth of the universe, the divide becomes fatal. Imagine a collapsing star. As it implodes under its own weight, the density increases, the curvature of spacetime intensifies, and gravity grows stronger. According to Einstein's equations, nothing can stop this collapse. Eventually, the star's core shrinks to a point of infinite density, a singularity where the laws of physics break down completely. But quantum mechanics forbids infinities. It insists that uncertainty prevents matter from being squeezed into a perfect point. Something must resist the collapse, or at least blur it. Yet when we try to calculate how quantum effects might modify Einstein's prediction, the numbers explode into infinities again. The same paradox appears at the beginning of the cosmos. General relativity tells us that the universe began as a singularity, an infinitely small, infinitely dense point that expanded into everything we see today. But no physical process can begin from infinity. Quantum theory demands that even the early universe must have had some finite size, some measurable energy, some uncertainty that smoothed the singularity away. Once again, the two descriptions contradict one another. To understand how deep this conflict runs, consider what each theory says about space and time. In general relativity, space-time is a flexible continuum. It curves, it stretches, it can even ripple as gravitational waves. But in quantum mechanics, space-time is a stage, a fixed background, upon which particles dance according to probabilities. Quantum equations assume that the geometry of space and time is static and well-defined. General relativity insists that geometry itself is dynamic. When you try to make the geometry dynamic inside a quantum framework, you find that it fluctuates violently. The gravitational field, now quantized, begins to jitter. Space and time themselves become uncertain, breaking the very assumptions that quantum mechanics depends upon. It is as if each theory destroys the foundations of the other. Physicists have long compared this conflict to trying to paint with fire and ice at the same time. The more you apply one, the more it undoes the other. Gravity wants smoothness. Quantum mechanics demands granularity. Gravity is deterministic. Given enough information, the future can be predicted exactly. Quantum mechanics is probabilistic. The future exists only as a range of possibilities until observation collapses it into reality. Between these two visions of the universe lies a gulf no bridge has yet crossed. For much of the 20th century, this gulf was tolerated rather than resolved. Scientists worked within the domains where each theory excelled. Relativity ruled astronomy and cosmology. Quantum mechanics ruled atoms and particles. There was no need to reconcile them until observations forced the issue. The first cracks appeared in the study of black holes. These mysterious objects are the perfect meeting place of Einstein's and Planck's worlds, places where immense gravity crushes matter into microscopic scales. When Stephen Hawking applied quantum theory to the curved spacetime around a black hole, he discovered something astonishing. Black holes are not entirely black. They emit radiation. This radiation, now called Hawking radiation, arises because of quantum fluctuations near the event horizon, the boundary beyond which nothing can escape. In the vacuum of space, pairs of particles and antiparticles are constantly appearing and annihilating each other. If such a pair forms right at the edge of a black hole, one particle can fall in while the other escapes, taking a tiny bit of energy with it. Over immense timescales, this process causes the black hole to evaporate. The result is beautiful and terrifying. It means that black holes have temperature, entropy, and a quantum description. But it also means that the information carried by everything that falls into them might be lost forever, violating one of the fundamental principles of quantum mechanics, which states that information can never be destroyed. Here, the two theories collide head-on. General relativity predicts that information vanishes at the singularity. Quantum mechanics insists that it must be preserved. Both cannot be right. This is the black hole information paradox, one of the deepest problems in modern physics. It is the arena where the clash between Einstein's and Planck's worlds is most violent, and it has forced scientists to rethink what they mean by information, time, and even reality itself. In trying to solve it, physicists have uncovered hints that space-time and gravity may not be fundamental at all. They may emerge from something deeper, from the way quantum information is organized in the universe. If that is true, then gravity is not an independent force, but a large-scale illusion, an echo of something more primitive. It would mean that Einstein's curved space-time is not a fundamental ingredient of reality, but a shadow cast by the quantum fabric beneath. The collision between relativity and quantum theory, then, may not be a dead end, but a doorway. A sign that we have reached the limits of both frameworks and must look beyond them to a new language of physics, one that unites geometry, information, and quantum mechanics in a single vision. But before that vision can be reached, the conflict must be understood in its full intensity. We must follow it down to the smallest scales, where the smoothness of space-time dissolves, and the equations themselves begin to contradict one another. That is where the next part of our story leads into the Planck realm, where gravity and quantum mechanics tear each other apart, and where new ideas begin to form from the ruins of the old. At the outer edges of thought, where mathematics strains against meaning, lies a scale so extreme that our deepest theories collapse under their own weight. It is the realm of the Planck length, the Planck time, and the Planck energy, the boundary beyond which our current understanding of the universe cannot go. At this scale, around 10 to the power of minus 35 meters, the structure of space-time ceases to be smooth. Einstein's geometry, once flawless, fractures under quantum pressure. The very concepts of distance and duration lose meaning. To speak of where or when becomes impossible, for the coordinates themselves are swallowed by uncertainty. To understand why this happens, imagine trying to measure the position of a particle with extreme precision. According to the uncertainty principle, the more accurately you know its position, the less accurately you can know its momentum. To confine it to a smaller region, you must increase the energy of the measurement. But if you concentrate enough energy into a small enough volume, Einstein's equations say that energy will curve space-time so strongly that a black hole forms. The region you are trying to observe disappears behind its own event horizon. Nature forbids us from peering deeper. The act of observation itself creates a gravitational boundary that hides what lies below. The smallest possible scale is not merely difficult to reach, it is physically unreachable. The Planck length is the horizon of meaning. At this boundary, the smooth curves of general relativity dissolve into quantum foam, a churning sea of uncertainty, where space-time fluctuates wildly. Tiny wormholes flicker in and out of existence. Micro black holes form and evaporate in fractions of a moment. The vacuum itself becomes a storm of geometry, folding and unfolding faster than any clock could tick. Every equation we have breaks apart in this chaos. General relativity predicts infinite curvature and singularities. Quantum mechanics predicts infinite energy fluctuations. When combined, The infinities multiply until mathematics can no longer describe them. The universe, as we currently understand it, stops making sense. Physicists call this the problem of ultraviolet divergence, the explosion of quantities at extremely small scales. It is a sign that our theories are incomplete. A true theory of quantum gravity must somehow tame these infinities, weaving geometry and probability into a single fabric that remains finite and self-consistent. For decades, brilliant minds have tried to repair the broken harmony between the large and the small. Some have sought to modify Einstein's equations, adding extra terms that might prevent singularities. Others have tried to quantize gravity directly, treating space-time as just another field. Yet every attempt has encountered the same wall of infinities. This is not merely a technical problem, it is a conceptual crisis. It forces us to ask what space-time really is. Is it a substance that can be divided forever, or is it made of indivisible quanta, like energy itself? If geometry can ripple and fluctuate, does that mean it has atoms, discrete building blocks, that combine to create the illusion of continuity? One clue lies in black holes. In the early 1970s, Jacob Bekenstein proposed that a black hole's entropy, the measure of its internal disorder, is proportional not to its volume, but to the area of its event horizon. Stephen Hawking confirmed this by showing that black holes emit radiation and therefore possess temperature. The entropy of a black hole, he found, is equal to its surface area divided by the Planck area, a patch of space-time, about 10 to the power of -70 square meters. This formula is profound. It suggests that the smallest units of information, the fundamental bits of the universe, are stored not within space, but on its surface. Each Planck-sized patch of area encodes one quantum of information. In other words, the world may not be three-dimensional in the way we think. It may be holographic, a projection of information written on a lower dimensional boundary. The smoothness of space-time could be an illusion, a shadow cast by a deeper layer of quantum information. If that is true, then the Planck scale is not merely a limit of measurement, but the pixelation of reality itself. The universe, when seen up close, would be granular, a cosmic mosaic of information units, each smaller than imagination can grasp. This holographic idea, first hinted at in black hole thermodynamics, would later grow into one of the most revolutionary concepts in theoretical physics. It suggests that everything we perceive as space, time, and gravity emerges from quantum information stored at the universe's boundaries. But before that realization took form, physicists faced the wreckage of their two greatest achievements. General relativity, the masterpiece of the continuous, could not survive the discontinuous world of quanta. Quantum mechanics, the science of probabilities, could not define the geometry it operated within. The two were like opposing mirrors, reflecting each other endlessly, but never meeting. In the search for a bridge, some theorists turned to radical ideas, extra dimensions, hidden symmetries, new particles, and new kinds of geometry. They began to suspect that our familiar four-dimensional space-time is only a projection of a deeper, higher-dimensional reality. This shift marked the beginning of a new era, the rise of theories that would treat the graviton not as a fundamental particle, but as a vibration of something more primal, a string. String theory offered the first glimpse of harmony between the quantum and the geometric. In its equations, the graviton appeared naturally, not as an afterthought, but as an unavoidable consequence of consistency. It seemed to say that the universe's contradictions could be healed if we replaced point-like particles with one-dimensional strings vibrating in multiple dimensions. For the first time since Einstein, there was hope that gravity and quantum mechanics could coexist without tearing each other apart. But that hope would lead physics into even stranger territory, into hidden dimensions, higher symmetries, and a universe that might not be what it seems at all. At the dawn of the 21st century, physics found itself in a strange position. Two of its greatest theories stood tall, flawless within their own domains, yet irreconcilable with each other. General relativity described the grand sweep of galaxies and the slow bending of starlight around massive suns. Quantum mechanics ruled the invisible world of atoms, electrons, and particles, smaller still. Both were tested, confirmed, and verified with exquisite precision. Yet at their intersection, in the heart of a black hole, or in the first instant after the universe's birth, both collapsed. It was not that either theory was wrong. Each was true, but only within its own horizon. Relativity told us that space-time is curved by energy and mass, that gravity is geometry itself. Quantum mechanics told us that nature is not continuous but discrete, that every field comes in quanta, that uncertainty is fundamental. Both truths were absolute, and yet together they could not coexist. At the Planck scale, their equations became a battlefield of infinities. Relativity's smooth curves collided with quantum theory's restless fluctuations. Energy densities grew infinite, timescales vanished, and the very idea of space as a continuous fabric dissolved into abstraction. Physicists tried to push beyond this frontier with every tool they had. They attempted to quantize space-time itself, breaking it into finite elements. They redefined gravity as a spin-2 field and tried to tame its infinities through mathematical tricks. They explored the behavior of singularities, wormholes, and virtual black holes, hoping to find a pattern. But all paths led to contradictions. The deeper they went, the more the universe resisted. The problem was not simply in the equations, but in the assumptions behind them. Both theories took space-time for granted, one as a continuous geometric fabric, the other as a fixed background for fields to play upon. But what if space-time was neither? What if it was not the stage of the universe, but part of the cast? What if the smoothness of geometry was an illusion emerging from something deeper and more chaotic below? Hints of that idea began to appear in unexpected places. In the 1970s, the study of black holes suggested that information and geometry were intimately linked. Hawking's discovery of radiation implied that black holes had entropy, and therefore microstates, hidden degrees of freedom that must somehow encode information about what fell into them. But where could those microstates live? General relativity says a black hole is defined by only three numbers: its mass, its charge, and its spin. Everything else, the details of what formed it, is lost. Quantum mechanics insists that information can never be lost. Somewhere, the universe must keep its records. The answer seemed to lie not inside the black hole, but on its surface. The entropy of a black hole is proportional to the area of its event horizon, not its volume. Every square of Planck area encodes one bit of information. This strange fact hinted that space-time itself might be holographic, that everything within a region of space could be described by information on its boundary. If that is true, then the universe is not built from points in space, but from bits of information. Space and time, in this view, are not fundamental. They are emergent, like temperature or pressure, large-scale averages of countless microscopic interactions beneath. The collision of theories thus opened the door to something radical. It suggested that the conflict between relativity and quantum mechanics was not a problem to be fixed, but a clue to something deeper, a signal that both were approximations of a more fundamental framework. In that deeper picture, space-time might emerge from entanglement, the quantum linkage between particles that persists even across vast distances. Entanglement could be the fabric from which geometry itself is woven. The curvature of space-time could reflect the pattern of connections between quantum states. Gravity could be a manifestation of information flowing through those networks. The mathematical seeds of this idea began to grow into bold new theories. The holographic principle proposed that the universe can be fully described by information stored on its boundaries. The ADS-CFT correspondence, a later refinement, suggested that a gravitational universe in one set of dimensions could be equivalent to a quantum theory without gravity in fewer dimensions. Geometry and quantum information, it seemed, were two sides of the same coin. But in the 1980s, before these ideas took root, a different theory arose from the ashes of failed unifications. one that promised not just a bridge between quantum mechanics and gravity, but a single framework for all forces and particles. It began with a simple realization: perhaps the building blocks of the universe are not point-like at all. Perhaps they are tiny strings, vibrating at frequencies so high that their length, roughly the Planck scale, defines the smallest possible unit of structure. In this theory, every particle we observe is a vibration mode of the same underlying entity. An electron, a photon, a quark, even a graviton, all are different notes played by the same string. The geometry of space-time, the forces of nature, and the matter within it all arise from the harmonics of these invisible filaments. For the first time, gravity emerged naturally from quantum theory. It was no longer an outsider. The graviton appeared automatically as one of the possible vibration modes of the string, not as a forced addition, but as a requirement for mathematical consistency. It was as if the universe had always been an instrument, and physics was only now beginning to hear its underlying music. Yet this new theory, elegant as it was, came with a price. It demanded extra dimensions, not 4, but 10 or even 11. It required a universe vastly larger and more complex than we can perceive, and it replaced the familiar geometry of Einstein with a higher dimensional landscape of possibilities, each corresponding to a different way the strings might vibrate. For decades, physicists have chased this vision, exploring its implications, testing its limits, and uncovering its beauty. But it is still incomplete. The mathematics of string theory is vast and subtle, and the energy scales it predicts remain far beyond our experimental reach. Still, it offers something that no other framework has: a vision of unity, one in which gravity and quantum mechanics are not enemies but companions, both arising from the same underlying symphony. The collision of theories, then, was not the end of physics. It was its rebirth. From the wreckage of Einstein's geometry and the strangeness of quantum uncertainty, emerged a deeper possibility that the universe is built not from matter or fields, but from vibrations, information, and relationships. The next chapter in our story follows that possibility into the world of strings, dimensions beyond the visible, and the realization that gravity itself might be the echo of a deeper, hidden rhythm woven into the foundation of the cosmos. The search for quantum gravity began in failure. Every attempt to merge Einstein's smooth spacetime with the granular world of quantum mechanics collapsed under infinities. Then, almost by accident, a new idea appeared, one that would transform physics. It began as a theory not of gravity, but of the atomic nucleus. Physicists, trying to describe the strong force, imagined that particles like protons and neutrons might not be points, but tiny vibrating strings. Each vibration corresponded to a different particle. The idea seemed elegant but irrelevant until the equations revealed something unexpected. Among the possible vibrations of a string was one that behaved exactly like a graviton, a massless spin-2 particle. Gravity had emerged from the mathematics on its own. That revelation changed everything. If strings could give rise to gravity naturally, then perhaps all of nature's forces and particles were simply different notes of the same underlying vibration. The universe could be a vast cosmic instrument, its every element, from light to matter to space-time, composed of harmonies played on microscopic strings. But the theory demanded extra dimensions. For its equations to be self-consistent, strings had to vibrate in 10 dimensions, 9 of space and 1 of time. The 6 extra dimensions the theory proposed were compactified, curled up so tightly that they were invisible, shaping the properties of the universe we perceive. Their geometry determined everything: the strengths of forces, the masses of particles, even the constants of nature. From these compact shapes called Calabi-Yau manifolds emerged the laws of our world. Each possible configuration of the hidden dimensions represented a different possible universe, an immense landscape of realities, perhaps 10 to the power of 500 in number. This idea led to a breathtaking possibility. Our cosmos might be one melody among countless others, each a different way the universe could have vibrated. In this framework, gravity is no longer a fundamental force. It is an inevitable consequence of string vibration. The graviton, the carrier of gravity, appears automatically, its existence required by the mathematics itself. The smooth curvature of space-time, described by Einstein, becomes a large-scale effect of countless interacting strings. To explain the deeper unity between the various forms of string theory, physicists discovered something even more profound. All 5 versions of the theory are connected as reflections of one greater whole, known as M theory. In 11 dimensions, the fundamental entities are not just strings, but higher dimensional membranes, brains, which can ripple and fold across the hidden dimensions. Our universe, in one interpretation, is a 4-dimensional brain floating in this higher dimensional space. Gravity is weak because it spreads across all dimensions, while the other forces are trapped on our brain. Beyond our perception may exist other universes, parallel brains, separated by dimensions too small or too warped to detect. In this view, space-time itself is not fundamental. It is emergent, a product of the interactions and entanglements of the strings and brains beneath. The bending of space-time is not a separate process, but the macroscopic reflection of microscopic vibrations. Even deeper connections emerged from the holographic principle. Born from the study of black holes, it revealed that all the information contained within a volume of space can be represented on its surface, suggesting that the universe itself is a hologram. In the context of string theory, this means that a world with gravity can be equivalent to a quantum theory without gravity living on its boundary. Geometry and quantum information are 2 sides of the same reality. Gravity, then, may be thermodynamic, not a fundamental force, but an emergent effect of information and entropy. The curvature of space-time could be the collective behavior of quantum bits, the geometry of entanglement. Mass and energy would merely change the pattern of that entanglement, and gravity would follow as the universe's way of balancing information. In this vision, everything is connected. Strings, brains, geometry, and information form one continuous web of relationships. Matter and energy, curvature and motion, all arise from the same underlying rhythm. Einstein showed that gravity is geometry. String theory suggests that geometry itself may be vibration, and the whispers of M theory go further still, that vibration may be only the surface of something deeper, where reality is not made of matter or energy, but of information itself. If so, then gravity is not merely the shape of space-time, it is the sound of the universe thinking. For centuries, gravity has been treated as something fundamental, a force as old as the cosmos itself, woven into the structure of existence. Newton saw it as an invisible pull, acting instantly across space. Einstein transformed it into the curvature of space-time. But in the 21st century, a radical new idea began to take shape, one that suggests gravity might not be fundamental at all. Perhaps gravity is not a primary law, but a consequence. Perhaps it arises from something deeper, from the hidden thermodynamics of space-time, from the quantum information that underlies reality itself. The seeds of this idea were planted by Jacob Bekenstein and Stephen Hawking. Their work on black holes revealed something astonishing. Black holes have entropy. The entropy of a black hole, they discovered, is proportional not to its volume, but to the area of its event horizon. Each patch of surface, 1 Planck area wide, encodes a single quantum of information. This finding shattered centuries of intuition. It suggested that the information content of the universe is not stored in its volume, but on its boundaries, a principle now known as the holographic principle. Everything inside a region of space can, in principle, be described by information encoded on its surface. If space can store information, then it may possess entropy, and where there is entropy, there is temperature, energy, and thermodynamics. That realization inspired a new line of thought. What if the geometry of space-time behaves like a thermodynamic system? In the late 1990s and early 2000s, physicists began to uncover hints of this hidden connection. The equations of Einstein's general relativity, they found, could be derived from the laws of thermodynamics if one treated space-time as a system with entropy and temperature. This was not coincidence. It suggested that the curvature of space-time might emerge from the statistical behavior of microscopic degrees of freedom, just as the pressure and temperature of a gas emerge from the motion of molecules. Then, in 2010, a Dutch theoretical physicist named Erik Verlinde proposed a bold and startling idea. Gravity, he argued, is not a fundamental force at all, but an emergent one, an entropic force, arising naturally from changes in the information content of space-time. In Verlinde's view, when matter moves through space, it alters the distribution of information in the universe. That change creates an entropic gradient, a difference in the number of possible microscopic states. The system responds to this imbalance by trying to restore equilibrium, and the result is what we perceive as gravity. In simpler terms, gravity could be the universe's tendency to maximize entropy, its drive toward greater informational balance. Objects move toward one another not because they are being pulled by an invisible force, but because doing so increases the number of microscopic configurations the universe can occupy. This idea reframes everything we think we know about gravity. The fall of an apple, the orbit of a planet, the bending of light near a star all may be emergent effects of deeper informational laws. In this picture, space-time is not a fixed stage but a statistical medium. Its geometry changes as the underlying quantum information changes. Mass and energy do not bend space-time through direct force, but by altering the entropy encoded within it. Curvature is the macroscopic reflection of microscopic information flow. The equations support this view. When Verlinde derived the laws of entropic gravity, he found that Newton's law of universal gravitation emerges naturally, not as a starting assumption, but as a thermodynamic consequence. In the same way that the ideal gas law arises from molecular motion, the inverse square law of gravity arises from the entropic behavior of space-time. If true, this would mean that Einstein's general relativity is not fundamental either. It would be a large-scale approximation describing the emergent behavior of a deeper quantum system. Space-time, energy, and gravity would all be secondary effects born from the entanglement and thermodynamics of information. Such a view brings physics closer to the frontier of quantum information theory, the study of how information, rather than matter or energy, defines the universe. In quantum mechanics, information is everything. The state of a system is encoded in a wave function, and the evolution of that system is the transformation of information over time. Entanglement, the invisible linkage between quantum states, defines the structure of the quantum world. The holographic principle and entropic gravity both point toward the same conclusion. Space-time itself might be a manifestation of entanglement. The geometry of the universe could be a map of how quantum bits are connected. Distances, curvature, and even the flow of time might arise from the structure of those connections. Imagine the universe as an enormous web of quantum information. Each connection between particles, each thread of entanglement, defines the geometry of space. When that network changes, space itself changes. When information flows, gravity emerges as the large-scale effect of that flow. This idea has profound implications. It suggests that the universe is not built from things, but from relationships, from the correlations between quantum states. Reality is not a collection of objects, but a tapestry of information, constantly rearranging itself. Even the passage of time may not be fundamental. It could be the universe's way of processing information, the measure of change in the cosmic data structure. To move forward in time is simply to move toward higher entropy, toward a more balanced distribution of information. In this view, gravity, thermodynamics, and quantum mechanics are all aspects of the same phenomenon, the dynamics of information. The curvature of space-time, the expansion of the universe, and the behavior of black holes are all governed by the same invisible logic, the universe's drive to organize and distribute information efficiently. What began as a force becomes a tendency. What began as geometry becomes statistics. And what began as space-time becomes information. Yet even this vision may not be the final word. Entropic gravity offers an explanation for the large-scale behavior of space-time, but it raises new questions. What are the fundamental degrees of freedom that carry this information? How does entanglement give rise to geometry? And what lies beneath the quantum network itself? These questions lead physics to the edge of its current understanding, to the boundary between space-time and the quantum foam beneath it. There, the smooth fabric of the universe dissolves into chaos, and gravity becomes the gentle average of something far more turbulent below. That is where our journey turns next, into the quantum foam itself, the bubbling foundation of reality, where space-time flickers, geometry dissolves, and gravity is born from the storm of the smallest scales. At the smallest scales imaginable, reality loses its calm. The smooth geometry of Einstein's space-time, which bends gently around stars and curves elegantly through galaxies, begins to tremble. The deeper we look, the more the universe shivers. This is the realm of the Planck length, about 10 to the power of minus 35 meters, the smallest possible unit of distance that can still have meaning. Here, the universe is not a serene fabric, but a boiling sea. Physicist John Wheeler called it the quantum foam. To him, space-time was not a rigid stage, nor even a flexible one, but a restless ocean of fluctuations. The energy of the vacuum, never truly zero, makes space-time bubble and twist at unimaginable speeds. Tiny wormholes flicker into existence, connect distant points, and vanish again. Black holes smaller than atoms appear and dissolve in fractions of a heartbeat. The very concepts of here and there, before and after, blur together. At this scale, Einstein's equations fail. The continuous curvature of general relativity cannot survive this storm of uncertainty. Space and time cease to be continuous quantities. They become probabilistic, a shifting foam of possible configurations, each bubbling briefly into being before collapsing back into the quantum sea. Every fluctuation of the foam represents an experiment in geometry. One moment, space-time might curve inward. The next, it might stretch outward. Wormholes could link distant regions, then snap shut. Virtual particles burst into existence and vanish, their fleeting lives creating ripples in the structure of reality itself. This is the foundation of everything. The stars, the planets, the galaxies, all emerge from this churning substructure. Gravity, in this picture, is not a fundamental interaction, but the large-scale smoothing of the chaos below. It is what happens when the random fluctuations of the quantum foam are averaged over vast distances and timescales. Just as the calm surface of an ocean hides the turbulence beneath, the smooth geometry of space-time hides the quantum storm that creates it. In the foam, nothing is still. Energy fluctuates so violently that the vacuum itself becomes a living entity. According to quantum mechanics, empty space is never truly empty. Virtual particles and antiparticles are constantly created and destroyed, borrowing energy from the vacuum and returning it in moments so brief that no law is violated. These fluctuations give rise to measurable effects, like the Casimir force, a faint attraction between metal plates in a vacuum, caused purely by the quantum restlessness of space. If this is what happens at the human scale of physics, imagine what occurs at the Planck scale, where gravity joins the game. There, every fluctuation in energy distorts space-time, and every distortion in space-time changes the energy field. The two feed each other in an endless cycle. Space-time becomes self-aware, a system that reacts to its own fluctuations. This is where the familiar rules of physics dissolve. Distances and durations lose meaning. The geometry of space-time changes faster than light can travel. Quantum fields and gravitational fields merge into a single entity that cannot be separated into parts. Many physicists believe that this is where the ultimate unification must begin, at the level where geometry and quantum theory are no longer distinct. Loop quantum gravity, one of the leading approaches, attempts to describe this domain by quantizing space itself. In this framework, space is made of discrete units, tiny loops of area and volume, each representing a quantum of geometry. These loops connect into a vast network, forming a spin foam that evolves over time. Space-time, in this vision, is not continuous, but woven from these microscopic threads. Each thread carries information. Each intersection encodes a piece of geometry. Together, they form a dynamic web that defines the shape of the universe. Gravity emerges as the collective motion of this web, the way a wave emerges from countless vibrating water molecules. String theory offers a different view of the same realm. In its picture, the foam is made not of loops but of strings, fundamental vibrations that ripple through the quantum vacuum. These strings stretch, twist, and sometimes join or break, creating the microscopic tremors that shape space-time itself. In both views, geometry and quantum information are inseparable. At this scale, even the concept of a point in space becomes meaningless. Points require exact position, but quantum uncertainty forbids exactness. Every attempt to define a position injects energy into the system, curving space-time so violently that a tiny black hole forms. Nature protects its smallest secrets by hiding them behind horizons of its own creation. This interplay between uncertainty and curvature defines the boundary of knowledge. It marks the horizon where quantum mechanics and general relativity finally merge not through equations, but through their mutual failure. Each theory breaks down at precisely the point where the other becomes essential. And yet, from that failure, a new vision emerges. The quantum foam is not chaos for its own sake. It is the seedbed of structure, the primal motion, from which space-time, gravity, and the universe arise. The foam's fluctuations, when averaged across scales, create the smooth geometry that Einstein described. Its self-interactions give birth to the laws of thermodynamics that govern black holes and cosmic horizons. Gravity, then, may be the great simplifier, the universe's way of averaging its own turbulence into something stable. It is the whisper of the foam smoothed by scale, the melody that remains after the noise of quantum fluctuation fades. If this is true, then the distinction between force and fabric dissolves. Gravity is neither a fundamental pull nor an independent law. It is the visible shadow of invisible motion, the calm echo of the quantum storm that underlies all existence. In laboratories and observatories across the world, scientists are now searching for signs of this hidden layer, the fingerprints of the quantum foam. Tiny shifts in gravitational waves, minute anomalies in high-energy collisions, subtle deviations in the behavior of space itself, might someday reveal the texture beneath the smoothness. The next great discoveries will not come from looking outward, but inward, not from studying galaxies, but from decoding the structure of emptiness itself. For the closer we look into the void, the more alive it becomes, and so we arrive at the edge of knowledge, where gravity ceases to be a force and becomes a story, the story of how nothingness gives birth to everything, how fluctuations become geometry, and how the quiet hum beneath reality becomes the world we see. The next step in our journey takes us into that search, into the experiments that are beginning to listen for the faintest tremors of this hidden world, the smallest signals that might finally reveal the quantum face of gravity. For generations, gravity was the one force we could feel yet never see. We felt its pull in every step, watched its power in the orbits of planets and the fall of stars, but its messenger remained silent. Then, 1 century after Einstein predicted them, the silence broke. In September of 2015, a faint tremor reached Earth, a vibration not of air or sound, but of space-time itself. 2 black holes, each dozens of times more massive than the Sun, had collided over 1 billion light-years away. Their merger sent ripples racing through the fabric of the universe. Those ripples were caught by the twin detectors of the Laser Interferometer Gravitational Wave Observatory, known as LIGO. The signal lasted less than a second. Yet in that heartbeat, it confirmed one of Einstein's boldest predictions: gravitational waves are real. These waves are distortions of space-time that travel at the speed of light. When massive objects accelerate, when stars explode, or black holes merge, they send out waves that stretch and compress the universe as they pass. Detecting them requires unimaginable precision. LIGO can measure a change in distance smaller than 1/10,000th the width of a proton. That first detection marked a new era in physics, the beginning of gravitational wave astronomy. For the first time, we were not just seeing the universe, we were hearing it. Every merger, every collision, every cataclysmic event adds its note to the cosmic symphony. Since that day, LIGO and its partner observatories, Virgo in Europe and Kagra in Japan, have detected dozens of such events. Black holes swallowing one another, neutron stars colliding, space-time ringing like a bell. Each detection refines our understanding of gravity on the largest scales, but hidden within those signals might be something even deeper, the first hints of gravity's quantum nature. If space-time is truly made of discrete quanta, if gravitons exist, then gravitational waves might carry subtle fingerprints of that microscopic structure. Tiny irregularities in their form, faint echoes in their interference, could reveal that the smoothness of space-time is only an illusion. Detecting such features, however, is almost impossible. The quantum of gravity is unbelievably weak. A single graviton carries so little energy that to detect one directly would require an instrument so massive it would collapse into a black hole under its own weight. Yet, physicists persist, because even indirect evidence could change everything. Future observatories are being built to listen more closely. The Laser Interferometer Space Antenna LISA, a network of satellites separated by millions of kilometers, will orbit the Sun, listening for lower frequency waves from supermassive black hole mergers. Pulsar timing arrays, using millisecond pulsars as natural clocks, are already detecting the slow undulations of space-time caused by vast cosmic events. Each of these instruments is a new sense, an extension of our perception into the geometry of the universe itself. Together, they may one day reveal deviations, anomalies that no classical theory can explain. Beyond these lies the realm of quantum experiments, tabletop setups where physicists try to observe the quantum behavior of gravity directly. Some propose using ultra-cold atoms, suspended and entangled, to detect gravitational fields too weak for ordinary sensors. If two quantum systems become entangled through gravity alone, it would be proof that gravity itself is quantum. These are delicate, almost impossible experiments. Yet they are being designed with the same patience that led to LIGO's triumph. Decades of silence preceded that first detection. Now, with new tools, we may hear gravity's faintest whispers yet. But even as experiments push outward, theory pushes inward. Physicists search for ways to detect traces of quantum gravity not by measuring gravitons, but by studying how space-time behaves at its limits near black holes, near singularities, in the earliest moments after the Big Bang. When two black holes merge, the resulting ring down the fading vibration of the new black hole encodes information about the nature of gravity. If that vibration deviates from Einstein's prediction, it could reveal the influence of quantum effects. Some even predict that the edges of black holes might not be perfectly smooth horizons, but slightly fuzzy boundaries, shaped by quantum information leaking outward. Others look to the universe itself. The cosmic microwave background, the faint afterglow of the Big Bang, may contain imprints of primordial gravitational waves, created in the first trillionth of a second after time began. Detecting those ancient ripples would open a window into the quantum birth of space-time. Projects like the Simons Observatory and future satellite missions aim to measure these patterns with extraordinary precision. If found, those primordial waves would be the oldest signal ever observed, an echo of the moment when gravity first emerged from the quantum foam. In parallel, quantum interferometers and entanglement experiments on Earth are being refined to probe gravity's subtleties. Devices that manipulate photons, atoms, and superconducting circuits could, in principle, detect how quantum states respond to gravitational curvature. Such results would bridge the vast divide between relativity and quantum mechanics, not through speculation, but through evidence. The search is not just for a signal, but for understanding a sign that the geometry of space-time is quantized, that information and curvature are one and the same. This pursuit pushes technology to its absolute limits. It requires silence deeper than silence, stability greater than stillness, and precision that approaches impossibility. It demands patience across generations. And yet, humanity has done this before. We have listened to atoms, captured light from galaxies billions of years old, and measured the heartbeat of space-time itself. Each time, what seemed impossible became real. Perhaps one day, a faint irregularity in a gravitational wave, or a flicker in an interferometer's data, will whisper the answer proof that gravity is quantum, that space-time is woven from discrete threads of information, that the foam beneath reality can be heard. That discovery would not just complete Einstein's work, it would transform our understanding of existence. It would reveal that every motion, every curve, every moment of time is part of a quantum conversation, a dialogue between geometry and information that has been unfolding since the universe began. The hunt continues, patient and relentless. Somewhere in the noise lies the smallest signal, the tremor, that could reveal what gravity is truly made of. And beyond that signal, perhaps, lies the final revelation that gravity is not a thing at all, but the shape of everything else. For more than 4 centuries, gravity has guided humanity's understanding of the universe. From Newton's apple to Einstein's curvature of space-time, from the trembling signals of colliding black holes to the quantum foam beneath reality, it has remained both the most familiar and the most mysterious phenomenon of all. It binds galaxies, sculpts light, and anchors time itself. Yet when we ask what it is made of, the universe answers only with silence. Newton described gravity as a pull, an invisible thread connecting every mass in the cosmos. He gave us equations that still send rockets to other worlds, but he never claimed to know what the force truly was. "I frame no hypotheses," he wrote, leaving the mystery open. Einstein replaced that thread with geometry. "Gravity," he said, "is not a force at all, but the curvature of space-time. Mass and energy tell space-time how to curve, and that curvature tells matter how to move." His theory transformed our view of reality. It explained the bending of starlight, the slow ticking of clocks near massive bodies, the expansion of the cosmos itself. But even Einstein's elegance left questions. If gravity is geometry, then what makes geometry exist? What breathes life into space-time? Quantum mechanics offered no comfort. It described a world of discrete packets of energy and probability, a universe of particles and fields, not smooth curves. In that quantum world, every force has a messenger. Photons carry electromagnetism, gluons bind quarks, W and Z, bosons govern the weak interaction. Gravity, by this logic, should have its own quantum carrier, the graviton. Yet after decades of searching, none has ever been found. The theories diverged. Einstein's universe was continuous and deterministic. The quantum world was granular and uncertain. Each worked perfectly within its own domain, but where they met in black holes, in the first moments of the Big Bang, the mathematics broke apart. At those boundaries, gravity refused to fit. String theory offered a bridge. It suggested that all particles, all forces, and even space-time itself emerge from vibrating strings of energy. One mode of vibration naturally behaves like a graviton. Gravity, in this vision, is not an add-on, but an inevitable note in the symphony of the universe. Yet the theory required dimensions beyond our perception, hidden geometries, shaping everything we see. It was vast, beautiful, and unfinished. Then came an even deeper suspicion that gravity might not be fundamental at all, that it could be emergent, like temperature or pressure, arising from the statistical behavior of microscopic degrees of freedom. In this view, gravity is the universe's way of balancing information. Mass changes the distribution of information in space-time, and the result, the entropic gradient, is what we feel as attraction. Einstein's geometry and Newton's force may be two expressions of the same truth. Gravity, is how the universe keeps its information in order. And beneath all of it lies the quantum foam, the seething foundation, where space-time itself flickers in and out of existence, where geometry and energy become indistinguishable. Gravity, then, could be the smoothing of that chaos, the gentle average of the storm beneath. Every theory, from strings to loops to holograms, points toward one unifying idea. Gravity is not made of anything. It is the structure of everything else. It is not a particle or a field, not a vibration or an equation, but the language by which the universe organizes itself. Matter tells space-time how to curve. Yes, but space-time is itself the memory of matter, the record of all energy and motion. Gravity is that record being read, updated, and sustained. When we ask what gravity is made of, we are really asking what reality itself is made of. And the answer, increasingly, seems to be information. Not information in the everyday sense, but the pure, mathematical essence of difference, the way one part of the universe can affect another. Information gives birth to geometry. Geometry gives birth to motion. Motion gives birth to time. And from time arises everything we know. In this sense, gravity is the whisper of space-time, the echo of energy, the memory of motion. It is the shape that information takes when it becomes real. If we could see the universe from outside, stripped of its light and matter, we might find that what remains is not emptiness, but structure, an intricate web of entanglement, a living map of information flowing and recombining. Gravity would be the curvature of that map, the way the network bends under its own complexity. So what is gravity made of? It may be made of nothing that can be touched, measured, or isolated, because it is the very act of touching, measuring, and connecting. It is the architecture of existence itself. In the end, every explanation brings us back to the same truth that Newton intuited, Einstein reimagined, and modern physics still chases. Gravity is the shape of reality. It is not an object within the universe, it is the universe's way of being. Look around you. Every motion, every shadow, every heartbeat, every orbit of every world is part of that same invisible dance. The apple that fell in Newton's orchard, the light that curves around black holes, the expansion of the cosmos, all are expressions of one law that is not made of matter, but meaning. Perhaps one day, when we have mapped the quantum foam and decoded the language of information, we will finally understand the fabric completely. Or perhaps we will only find deeper patterns, endless layers of emergence. Either way, the question will remain eternal. What is gravity made of? And the universe will answer, as it always has, not in words, but in motion. Because gravity is not something the universe has, it is what the universe is.